So welcome everybody. Postgres internals through pictures. My name is Bruce Momjian. I work for EnterpriseDB. Been with them for 9 years. Obviously do a lot of enterprise deployments of Postgres. But my primary job is actually to work with the community. I've been doing that since 1996, so I'm in my 19th year. Sounds crazy, but true. And one of the things that really got me excited about Postgres in 1996 was the ability to see inside the source code. I was working at that time as a database application author. So I wrote database applications for law firms, and I was using commercial databases, particularly Ingress and Informix at that time. And it always perplexed me, enticed me, made me curious. How does this SQL get interpreted by the database server? How does it know what I'm asking? How does it optimize it? All these sort of very complex things that I didn't really understand. So I sort of set out to install a version of SQL on my server. At that time, I think I was running BSD Unix or AT&T Unix. I can't remember which one. And the only one that was really very similar to the commercial databases I was working on was Postgres. So this has always been an area that's enticed me and sort of kept me interested in Postgres. Tom Lane actually became interested for a similar reason. We worked together on some of the early optimizer improvements, or bug fixings actually, very early on. So this is a topic near and dear to my heart. I'm very pleased to be able to present it to you. This tutorial is 3 hours. We do have about 20 minutes for a break in the middle. So somewhere between an hour and a half in, we'll take a 20-minute break, and you can get up and relax. So, but again, I'm going to try and pour as much information out as I have about Postgres to you. We will be using this presentation. Actually, we have a, you can actually download the presentation right now at this URL right here. So momjian.us presentations. I will be using more than this presentation. So this is the presentation to start. But depending on the type of questions you ask, we will be sort of moving into some other things. I have presentations on the optimizer, presentations on how we do locking, how the data storage format is made. I have a presentation on MVCC. So there's a lot of internal stuff that I've written over the years that we'll be pulling from. Again, all at that URL. So if you see a new slide come up, it's basically from the same place. And I also wanted to be interactive because, again, this is a tutorial, so we want to have people sort of asking about things, and we can probe into whatever detail that you consider to be appropriate. And again, I'm excited to be doing this. I am appreciative you're all here on time. It's kind of surprising. Everyone's here early. I was like, wow. So that's kind of a shock to me, but I'll get used to it. Again, this presentation has been developed over a number of years of sort of honing it and adding additional capabilities, and then we're going to spend some time toward the end diving into other presentations. And again, I would do encourage you to ask questions. Some people have said when they hear me lecture, it feels like they're back in college. There could be some truth to that. I was in education for 5 years, so I'm sort of used to doing this. Used to answering questions and sort of doing stuff on the fly. So let me ask if there's any questions before we get started about anything. I'm excited to be here. Last night I spoke in Seattle. We had a user group there, and we had 31 people at that user group, so that was really neat. And then Thursday night I'll be speaking in Atlanta, another user group, sort of my huge run to this week. And hopefully I'll be home most of December. So. I'm looking forward to that, and most of January probably I'll be home. So it's been doing a lot of traveling. I was in Vienna, Moscow, Prado 2 weeks ago or so. So again, there's a lot of excitement, a lot of activity in Postgres. That's why while you're here, this is sort of a big conference for us. Very exciting to be having it in the San Francisco area. I know a lot of you made great sacrifices to be here in terms of time and everything, so hopefully this is going to be a very well-used piece of your time. Again, the types of things we're going to be talking about are things that are pretty exotic, pretty esoteric, and I'll be glad to explain them in whatever detail you'd like. Okay. Let's just start with this presentation, and again, as we ask questions, we'll kind of go into additional things. So we're going to start with this query. This is a very simple query, and we're going to basically dissect that query down. The first thing you're going to realize is that it uses sort of the fundamentals of SQL. There's one table involved here. There's no joins. There's one where clause with one constant compared to one variable, we call it, or one field, and we return one row. And the reason I'm bringing this out is because the concepts of one relation or one table, one variable or one field, one constant, and one returned column are actually pretty fundamental when we start to look at the way that SQL interprets things, because again, we have to think of it not as the way a person who's submitting it, but as somebody who actually has to understand it. So we have to actually build all the infrastructure into Postgres so we actually understand what we're getting, and that's why we use this very simple SQL to get started. Okay? So let's suppose we have an application, and it basically issues this SQL, and then we basically get a result. In this case, it turns out there's actually just one row that comes out. So everything is sort of one table, one column, one where clause. And again, it's very simple, and we'll be showing you more complex examples as we go forward. And what we're going to be looking at basically is this part in the middle. So between the time the query is issued and the time the result comes back, what actually happens? And the first thing that happens is that the client application effectively has to call some interface library that knows how to communicate with Postgres, because Postgres being a database server, it's a separate process that sits outside of the application. Now, if we were using SQLite, for example, the application and the database would be in the same process space. Okay? But that's not obviously true here. The database server is a separate process started by PGConf or started by the postmaster, and it's running separately. So we have to have a way of communicating with it, and the way we communicate with it is effectively to call some interface library. Now, this interface library could be JDBC, it could be ODBC, but in this case, it's actually the C interface library that's called libpq. And I'm sure many of you have heard of libpq before. Effectively, what libpq is a way for an application to say, I want to send a command to the server. How do I do that? Oh, I have a function call, and effectively it calls a function call. In this case, the name of the libpq function is pqexec. Many of you might be confused why it's pq. Well, technically, and somebody actually asked me about this in Seattle yesterday, originally, Postgres was not written in SQL. It didn't understand SQL. It understood another query language called Quell. How many of you have heard of Quell? Wow. Okay, we got a couple of them. Good. So Quell was sort of the competitor to SQL. I believe that IBM was the push behind SQL, and Ingress was the push behind Quell. Over time, SQL kind of took over. But actually, the interface library, the libpq, actually the PQ in libpq stands for PostQuell, which is what the Postgres language at that time was called. And it was never changed because the interface never changed. In other words, the same application API that was used with Postgres back in the early 90s is pretty much the same API that we have available today. That's why it's called libpq. So what actually happens is the application calls an interface library. In this case, there's a specific function called pqexec, and it sends a string here. Now, you might be saying, well, OK, this is if I write the application in C, then it's going to call libpq. But what if I'm writing in Perl or Python or Ruby? Well, in fact, most of the scripting languages that people use are built on top of libpq. So when Perl or Python need to communicate with Postgres, they don't understand the wire protocol. They pass that query request down to libpq, which then does the network activity and all of the protocol on top of it. So effectively, pretty much every language except ODBC to some extent and JDBC use libpq. JDBC doesn't use it because it's a type 4 driver. It's a pure Java driver. So you can't obviously use, you can't have a type 4 driver that uses compiled C code. But an ODBC kind of uses libpq now, and pretty much everything else uses it. So even though you might not be using C, you still may be using libpq. The reason that's also important is because if you look at the libpq manual page, there's a whole bunch of things that libpq can do, like password storage and environment variables and stuff. And people are like, well, I'm using Python. That doesn't, but actually it does, because all the interface is still happening with libpq, so passwords management, pgpass, and the environment variables are actually all understood by Python programs because internally they're using the same program underneath. Okay? And effectively all you do is you've taken this string and we've made a C representation of that. The \n's effectively represent new lines. Okay, so we're kind of walking our way down the stack here. Let me ask for questions at this point, if anybody has any questions or things they want to know. Okay, so I realize it's still kind of basic. So this is the next step. So we've actually got our application code. It's called the libpq library, and the libpq library understands the protocol and understands how to send the query across the wire to the database server, in this case represented in what else? Light blue, right? Postgres blue. And then we basically run the query over here, and then we send a result back to libpq. libpq then allows me to pass the result back up to the application, okay? So what we're actually looking like is we're saying, okay, we understand the application, we understand it's calling the interface library, whether it's JDBC or libpq or something else. It's sending a query back and it's sending back. But actually, what does that look like? So here's an example of a TCP/IP packet, which was dumped, I think, using TCP dump. And you can actually see the query right here. Right here it says, Q select first name from friend where, and you can see all the hex right here. The OA is the new lines, okay? And the Q is actually a special letter. Every protocol, every message that gets sent to the server, the first letter is like an indicator of what type of message this is. And obviously Q would be, I'm a query. And that's how you identify, oh, here comes a query. Okay, so the wire protocol has a whole bunch of letters it assigns, Q being the one that says, here comes a query. Okay? And then once it arrives at the server, it's going to execute the query. It's a whole bunch of stuff's going to happen inside, and then it's going to return the result and come back. So what we've now gotten to the server. Now we're going to open that part up, and we're going to say, okay, I got the query to libpq. libpq sent it across the wire. It's gotten accepted by the server. What happens between the time it's accepted and the time I return my result? Okay, and the answer is a whole lot. This is actually a dump that you can get yourself if you enable some of the logging settings. And you can actually see that this little simple query, which you would think was like super easy, actually expands to this humongously complex structure that gets passed around in the server. And actually, this is not specific to Postgres. Effectively, all of the database servers have this same sort of architecture where the query comes in, whole bunch of stuff happens, and then the result comes back. And it's obviously designed to be super efficient and super performant. And what we're going to do is we're going to dig into this, and I'm going to show you exactly what that looks like. All right? Any questions so far? Wow. Okay. So here's the first stop. So the first stop of our query is to actually generate something called a parse tree. Okay? If you actually look back here, you can actually see the word parse tree right here, although it's kind of small. Okay? And then we have some other stages I'll talk about later. So the first stage is we have to take the query and break it up into pieces, because of course it doesn't really understand a query. There's no like knowledge in the server. It's just running a program, right? So we have to make a program that effectively understands almost arbitrary SQL language. And this is an example of sort of some of the internals. And you can see it looks a little like JSON, where it's got a kind of a key value kind of set up there from the colors. And then you even got nested structures, which sort of look like nested JSON. It's not JSON, but you kind of get the idea of that's what we're actually looking at. It's a sort of a nested key value type of structure. In this case, it's written in C. Okay, so this is kind of a big view of what's going on, and I think this is pretty illustrative. And again, this is not Postgres specific. Pretty much every database server has a similar set of stages that things have to go through. So effectively, you have up here at the top, you have the postmaster. That's the sort of server listener for Postgres. The thing when you start Postgres, you start something called the postmaster that's listening for connections on whatever port you define. By default, that's port 5432, but again, it could be any port. Okay, and then you have Libp. Then once you've authenticated, we create a sub-process called Postgres. And Postgres is the dedicated process that is responsible for answering queries for your particular session. Okay? In this case, I've shown two processes. This is one Postgres process. This is another Postgres process. And once the process starts, effectively, you're communicating with that process, in this case, using libpq or JDBC or some interface that understands the wire protocol for Postgres. Probably the first thing that people kind of see when they see this slide and I start talking is they realize that Postgres is process-based. So it's not running separate threads inside of one process. It actually is creating a separate process. That had performance impact on Windows. It still does. On Solaris, it used to. But by and large, most of the Unix operating systems, a thread, a process, it's kind of got the same amount of overhead. The process-based model has a bunch of advantages for us in terms of isolation, in terms of reduced locking, particularly for things like memory allocation and so forth. So effectively, the way Postgres does things, and again, I have a separate presentation for this, is the idea we have processed local things that we happen in their local memory, and then we have a huge shared memory segment where we put things like shared buffers and locks and so forth. And again, I have a presentation. We can talk about exactly how that works if people are interested. So let me I haven't gone to the blue square yet, but let me stop there and ask if for any questions that people might have. Yes, sir.
Sometimes when we want to stop a query,
yes.
long-running query,
right.
Resources, it doesn't stop right away.
So the question is, if you have a query that's using a lot of resources and you want to stop it, it doesn't stop right away. So there's actually two reasons for that. We could effectively, because it's a process-based model, we could, at the Unix prompt, just kill -9 the process, right? So that's an option, right? The problem with that approach to stopping things is that effectively, because so much of what Postgres does deals not only in local state, but in shared state, in shared memory, if we kill -9 a process, that process could be in the middle of manipulating certain shared memory statuses. And if a process just disappears, which is what effectively kill -9 gives us no way to clean up, it just pulls the roots out, the server will actually restart because it says, oh, one of my processes, which might have been doing something super critical in shared state, has now disappeared, and therefore I'm going to just restart all my sessions because I can't be sure anymore that shared memory is actually still accurate. Okay, so that's what we don't do. What we do is we effectively, when somebody sends a normal signal as documented or uses PG cancel backend or PG terminate backend, we send a signal effectively to the postmaster. The postmaster sends a signal to the child, and the child has signal handlers that again, they immediately see the signal, they acknowledge the signal has been received, they set a Boolean variable, and then at various places in the code where we know it is safe for that session to terminate, we will check for that global variable. And if it's set, we'll exit right away. The reason it takes a while is that sometimes you're in the middle of something that's critical and you can't do it, so therefore we got to wait a little bit for it to get farther down and then terminate ourselves when we know we're not going to interfere with any other session. So that's why it takes a while. We still get reports every so often where somebody says, I did a terminate backend and it didn't cancel. And what happens in those cases is that we've got some very time-consuming area of the code where we're missing a check. And I would say every release or every other release, we're having to add like 1 or 2. They're like, oh, we didn't have it here. Oh, we didn't have it there. And then we have to kind of add it. In most cases, it terminates right away. But there have been some cases that people are identifying. And we're getting better. I think, for example, sorting was one. There was a particular area of the sort where we weren't catching it. But you always do get that delay because we can't just stop it and be sure that it hasn't make sure that it cannot be corrupting something else. And that's why that delay happens. Does that answer your question? Yeah. Yeah. Other questions? Okay. Yes, sir.
So since it would be process-based and it's by itself, what mechanism does the query process and the postmaster, how do they talk to each other?
So the question is, because it's process-based, how do the sessions talk to the postmaster effectively, or how do you coordinate everything? So there's really 2 methods. The one method is that we have a shared memory segment, which I have a presentation about, and hopefully we'll get to, that actually takes the big shared memory area and breaks it down to pieces. And every session is attached to that same shared memory area. So effectively, if I want to lock and you have it, I go to sleep on your lock. We use semaphores. If I need to go to sleep for a long time on a lock that you have, I'll go to sleep on a semaphore. When that session finishes with its lock, it'll wake up everyone waiting on that semaphore. We also obviously have network communication. So when you do a query cancel, you effectively send a message up to the postmaster, and the postmaster sends it down to the session you want to kill. So there's kind of this. So you're looking at some cases it's shared memory, the communication. Some cases it's semaphores. And some cases it's actually a network connection from one session up to the postmaster saying, hey, I just got a signal, and you got to send a terminate to that child, and then wait for that child to effectively register the global variable has been set, and then either cancel that query or terminate that query. Does that answer your question? Yeah. Okay, yeah. So it's kind of hokey. If we had everything in one big thread, one big process with a whole bunch of threads, some things would be easier. For example, parallelism would be a lot easier if we went that direction. But historically, having known what Informix did, Informix 5 was a process-based, and Informix 4 was a process-based. And Informix 6 was going to be that new thing. This is back in the 90s. But Informix 6 was going to be parallelized. So you're going to be able to do parallel index builds and a whole bunch of things that they thought, oh, we're going to be able to do this parallelism. And what they did was they just took the process-based architecture, they made it threaded. The problem was in Informix 6, and even to some extent in Informix 7, unless you had multiple CPUs, it was actually slower than what you had before. Okay? And it was actually, Informix 6 was so buggy that they ended up aborting Informix 6. Everyone went back to Informix 5. And then when the Informix 7 came out, it took like 2 years to stabilize. Any of you working in Informix at that point? Yeah, it's embarrassing, right? It kind of almost pretty much killed the company. Because when you're getting a bug fit, when you know there are 3 bugs, and you've worked with Informix and you've worked around them, and then the next release, they say those bugs are fixed, and then you put in the next release, and it's true, the first 3 bugs are fixed, but now you have 3 more you didn't know about they're new. And if you go through that a couple iterations, you just stop upgrading. Because you've dealt with all the bugs you know, and you don't really want to spend time diagnosing a brand new set of bugs, right? So when people take that attitude, then effectively the software is mothballed because nobody wants to upgrade it anymore. So I think the lesson here and the way we're going about parallelism now is, yeah, we'd love to have parallelism, we'd love to have a whole bunch of things, right? But we're not, we have to admit that there's going to be downsides to changing an architecture. And effectively, when I start to go through this blue area, you're going to see that the majority of what a server does to process a query is local. It has there is a component of shared, and I'm going to show you that as we get into this other slides. There's a component of shared, but effectively, when you're parsing something, when you're optimizing it, when you're executing it, when you're declaring variables, when you're sorting, all that stuff effectively is local. And to do that all in a thread, where every time you allocate memory, you got to lock something. Every time you actually add a whole bunch of overhead that really doesn't gain you a lot. Threading is really good for very lightweight activities. Parsing a query, it's not a lightweight activity. It's actually a very heavy activity. So it's not like you're going to sort of, let's shoot off a thread to run a query. No, the majority of work for a query is local and it's very expensive. So I think threads are great with GUIs. Threads are great when you have a lot of lightweight work that you not need to do like network processing or something that's very well defined. But queries are fairly heavy. And we're probably never going to, we don't anticipate any need to change the architecture. And some open source people who have gone the threaded route have actually asked me, well, how do you do this? And we say, well, we did process and we shared memory and we kind of split apart the one part you want to share and part you don't. And he said, yeah, I think in hindsight we should have gone that way too, because the threading, programming in a threading environment and the overhead of a threading environment is not trivial. And the process-based model gives us a lot of advantage, a lot of safety. I can kill a session very easily and know that everything is going to be cleaned up because the operating system takes care of it for me. The only downside I say is process creation on Windows is probably the biggest downside to the lack of threads. Other questions? Yes? Process is created per connection. You can use connection pooling, and therefore you're not doing that overhead all the time, particularly on Windows. That would be good. If you're creating a lot of really short-running processes, again, connection pooling probably going to help. But even if we had threads, it's not even the creation of the process, it's all the startup we have to do. That if we use pooling, we get rid of that. And if you're doing a lot of short-lived stuff, the connection pooling is a help. And even if we had threads, it wouldn't necessarily fix that. Because the connections stick around and then they go away after a while. And the system gets in, pretty like PG Bouncer, the system gets into a good rhythm where you get some very good throughput with a pooling option. Other questions? Okay, so let's having talked about that top part, let's talk about this center part, and then we're going to blow it up. Again, this is not specific to Postgres. This is very standard in terms of how database servers work. Effectively, when the query comes in, the first thing you have to do is to parse it. So, and I'm going to go into detail about how that happens, but until you parse it, until you know what it is, until you know whether it's a select or an update or delete, until you know effectively what it's asking you to do, there's nothing else you can do. So in fact, what you're going to find is that it's very hard to parallelize this process. It's really very you have to kind of go from one step to another. You can't run the executor part while you're parsing. You can't optimize it while you're parsing or it just doesn't work. So effectively, there's not a whole lot of parallelism in here. I know we have a whole bunch of work we're working on with parallelism. Robert Haas from EnterpriseDB committed parallel scan last week. So there's a lot of activity and interest and excitement about parallelism in Postgres. But effectively, there's probably 12 or 15 areas we can parallelize. Sorts, joins, aggregates, foreign data wrapper, sequential scans, partition activity. So there's probably 10 or 12. But in general, the basic requirement of what it does is pretty serial organized. You have to parse the query to find out what it is. If it's a utility command, meaning like a create or a copy, it goes to a separate part of the code, which we call the utility section, and there's a whole bunch of boatload of code in there that handles pretty much everything from alter table to copy to vacuum, all right? But if it's not one of the utility commands, it basically falls into the main part of the parser, which effectively goes through the rewriter. This is the part that handles things like views and rules. Then it goes into the optimizer, which is actually two parts. There's one part that actually generates all the possible paths that can access this data. And then the cheapest plan is chosen, and we generate something called the cheapest path is chosen. We generate something called a plan, and the plan is then fed into the executor. The executor executes the query, and then we go back to the parser again. So you can see it's a very sort of serially oriented, go from one step to another type of process. And I'm going to show you these pieces in detail so you can kind of get an idea of how that goes, and then we can branch off into other areas. I think already there's interest in seeing what's inside a shared memory. I have a very good presentation about that, and I'll be glad to show that when we get there. So Any questions about sort of the basic structure? Yes?
After execute plan, when it goes to parser?
Yes, so after basically what happens is the query comes in, and if it's not a utility command, effectively it's an insert, update, I'm sorry, it's a select, insert, update, or delete. What's interesting is that those 4 commands run through the same code path. So think of it this way: select selects rows and returns them. And an update selects rows and updates them. A delete selects rows and deletes them. Insert's kind of an outlier because it's kind of doesn't select rows, it adds rows, right? But if you're doing insert select, then of course it is selecting rows and inserting them, right? So effectively what we're doing is we do the rewriting part, we generate the paths, we find the optimal path, we generate a plan, the plan gets executed, and then it basically goes up and waits for the next input from the user. And it might hang there for a while waiting for another request to come. Okay, so it's basically just in this big loop all the time. And if you look at the source code, you can actually see the loop. It's just going around, kind of going through this process all the time. In fact, there's another slide now that people are interested, I will show it to you real fast here. Again, I'm going to go to my website, and actually, I'm going to do a search here. And let's see here, 2012, okay. There we go, where is it? Right. No, actually, hold on, I have it here. I'm sorry, I have it here. I know I can't remember everything I have, do I? No, it's not there. Hold on, I'll find it. I'm trying to remember what I called it. Well, I'm going to look it up. I'm going to look it up during the break, and I'll find it for you. It's basically a big chart that shows everything kind of going through the parser and the optimizer and the executor, and actually mentions the SQL function names, which might be interesting. But I'll find it when we take the break for snacks. Other questions?
Can you also refer to how you have refer functions to code?
The function, that's what I'm going to show you after the break. Yeah, it's kind of a big circle, because it basically just goes around all the time. Anyway, I thought it was kind of interesting. I can't remember what I call it at this point, so I will find it. Yes, sir.
Are we going to focus in on those 2 steps before the end where we generate the path?
We're going to focus on everything. Okay. Yeah, I'm going to talk about the parser. I'm not going to talk too much about the rewriter because that's pretty mechanical. But I have a separate presentation just about the optimizer. Okay, and we can cover that one today as well. And the executor, again, is pretty boring because it's just basically a recipe state machine that goes through. So there's not a whole lot there. To me, the optimizer and the parser are probably the 2 most interesting areas. Other questions? Mm-hmm.
Would you say that the optimizer is the part of the process that is mostly different from other database servers? You say at the beginning the architecture is pretty similar to other vector databases.
So the
optimizer is the thing that is like special about each different database.
So the question is, what is different about Postgres from other systems? I would say none of this is really different from other systems, honestly. They all have this exact flow. And I don't think Postgres is unique pretty much in any of this. Postgres becomes unique when you look at the object relational aspects, the ability to add data types, the ability to plug in new capabilities into Postgres. But this part is pretty generic. If somebody from Oracle came and they looked at this chart, they'd say, yeah, I get it. That's exactly what we do, or Informix. It would be exactly the same. Now, I can't see what they do because they don't have published source code, but in general, this structure would be very familiar to you. There's nothing, I don't think there's anything unique about any of this. This is pretty generic. So the nice thing is, even if you don't use Postgres, use another database, it's pretty much going to be the same process. Other questions?
From application, we have dynamically the variables are passed. So using PGConf, can I see the actual query that they're trying to?
So the question is, if you're using prepared statements, can you see the query that's getting executed? So the answer is no. The way that a prepared statement works is effectively you're sending those constants over and you're naming a prepared statement. Only in the server do you see that name. You see the actual query. So if you look in the server logs, you can see those queries. But you would not see them in the client or in the network traffic because the client doesn't really keep track of prepared statements. It's only really done in the server. Other questions? OK. So let's take a look at the first part of the parser. The first part of the parser is effectively something called a scanner. I'm not sure how many of you have sort of traditional computer science background, but effectively scanning is a very common, well understood aspect of pretty much any programming language that has a syntax. So what scanning does is it takes the string that's been supplied by the server and it breaks it up into what we call tokens, or words, if you want to think of it very simply. Okay? This is the scanner for an identifier. So this would be a table name, a column name, something like that. Okay? And it's effectively saying an identifier is a letter followed by a letter, an optional letter or digit. Okay? And of course, underscore is included in that specification. And what this code actually does is when you have an identifier coming in, it actually does some lookups into a lookup table, a binary search basically into a list of keywords. And it will return either the keyword value or it will return the identifier as a string. So for example, if you use the word select, that's a keyword. If you use the word where, that's a keyword. If you use the word employee, that's not a keyword. Okay? And one of the jobs of the scanner is effectively to pick apart when something comes in as a token, separated by white space, for example, not in a string. We identify, is this a keyword or is this just a generic string which could represent a table or column or something like that. Okay? The other thing it has to do is to identify numbers. So here is a pattern for a digit. Here's the pattern for letter, which we used right here. This letter pattern is actually listed right here with the list here and the underscore. Letter or digit, again, very similar. Here's an integer, which is a digit followed by more digits, right? Pretty easy to understand. Decimal and real are pretty hairy because you've got exponents on the end and all that other weird thing. And actually, when you have an integer coming in, what the scanner is going to do is going to call string to long, and it's going to try and convert that to what we call an I-const, which would be an integer constant. Okay? If we can take that token in and we can convert it to an integer, great. We're going to actually return as integer. If we can't, we're going to make a copy of it and we're going to call it a floating number. Again, it just sort of, that's all we can do. It's probably a set of digits that's just too big for an integer. So we have to punt on that one. A decimal, that's going to come in just as a string, and an f-const, and the same thing with a real. They're coming in. So this is our first process with the parser, is to take that query and break it up into tokens. Okay? Here's an example here. Here we have the same query we talked about before. Select first name from friend where age equals 33. And you can basically see it's broken them down into individual pieces. And that's how the parser, that's how the scanner is going to output its information. Once the scanning is done, we actually go into a second area of the parser called the parser, or the grammar. is a better your term for that. This happens to be the grammar for a select statement. So the thing that really identifies this as a select statement is this keyword, this word select. Remember I showed you here, when the identifier comes in, we look it up in a list of keywords. So that word select, it has special meaning. It's not, it knows, the system knows that select, that's not a name of a table, that's not the name of a column. That has got to be a keyword, and it identifies we're about to do a query, a select query. And then you have a whole bunch of other references to other grammars for from, for where, and effectively the whole job of this grammar parsing is to fill in something called a select statement node, which again, very C-oriented. Actually, it's Lisp-oriented because originally Postgres was written, some modular parts were written in Lisp. So we basically stuff a structure here, target list, from clause, where clause, and again, these dollar signs represent the positions. So this is $1, $2, $3, $4, $5, $6. Here's $5 from clause. Here it says from clause $5, right? Very easy to understand how you're basically taking the tokens in, you're scanning them, you're making tokens out of them, and then based on the grammar, you define what order those tokens will appear in, and then you basically are loading up this structure, okay? And effectively, this is the select statement structure that's referenced here, and you can see a whole bunch of things that look very similar. Here's our from clause, here's our where clause, here's our group by, here's our having, here's our sort clause, here's our limit clause, here's our for update clause, here's our distinct clause, here's our temp clause, here's our into clause. So you can kind of see pretty much every clause that you can optionally have in a select has a separate member of this select statement structure. Okay? And then and here's an example of a parse coming through. So here's a token of select, and you can see it's entering the select token. Then it's looking for an identifier. Then it's got the word from. Is there an indirection? Is there an expression? It keeps going. Here it's looking for an into clause. So it keeps looking in the grammar to see, do I have a match for the word from? And it's going to keep looking and keep trying until it finds one. Here's it kind of mixed together. So here's the token select. You can see it kind of coming in. And here it's still looking for a from. It doesn't actually find a match. There's more down here that eventually would match the from. Okay? There's some other structures here. Obviously, I'm using a very simple case here. You can have multiple tables. You can have multiple column names. We do have sort of a list structure that allows you to basically have a list of things. So even though I've shown you a very simple case, there's some very sophisticated ones out there. Here's sort of the API we use to manipulate lists in Postgres. We have something also called a range table entry. This is a representation of a particular table. So every table reference gets a range table entry, which again is used to kind of support the query that you have. We also have var entries, which represent particular variables or column names referenced in that particular query. Target entry, which is a return value from the select. So if you say select star, that's a target entry. Okay? And the ultimate goal of all of this from the parser is to fill in something called a query structure. This is basically where we stop and leave the parser. What this is it represents sort of the holistic view of a query. We don't know whether it's a select, an insert, or an update or delete, but this command tag here tells me. And then I have pretty much clauses for everything that could possibly be in an insert, update, delete, or select. That is from, temp, limit, joins, markers, aggregates, a portal. So all of the things that I could possibly have. So the whole goal of the parser is to basically stuff this thing. Okay? And what happens at the end of this is this query thing gets passed to the next stage, which is the rewriter. Okay? So all that parsing, all that scanning is really just trying to fill this in. It's not doing anything. It's checking for syntax errors. Okay? It's checking for things that are misspelled, or if you reference a column that doesn't exist in a table, this is where you identify that. Okay? So it's basically trying to take that query that you sent, which is usually much complicated than the one I gave you, and distill it down into something that can be represented in a really atomic way in the computer that we can then pass to the later stages. All right? Questions about this? Yeah. A range table is actually a phrase that comes from the time when we had Quell. So in Quell, you would say range of X, range of table is A, or you would actually use the word range. A lot of the stuff internally to Postgres is related to relational algebra, so more formal mathematical kind of proofs. So when we define a range table, we're effectively defining a variable, well, no, it's not a variable. It's a collection of objects that has rows associated with it, all right? So it could be a table. It could be a data source of some other kind. It could be a function that returns multiple rows. So a range table is effectively just a representation of an abstract collection of rows. And so if you have a select that has one table in the from clause, it's going to have one range table entry. If it has two, it's going to have two in the range table entry. And effectively, the way the var part works is the var actually references, it's kind of hard to see here, but effectively the var, so when I say select first name from friends or whatever, I'm actually saying I want the first var of the range table that I reference. So they're basically numbered. So you have range table 1, 2, 3, 4, and the first one is the first table and so forth. So you would say range table 1, column field 2. And that's the second column in that range table that you've defined. So that's how it all kind of comes together. Internally, when you say select star, you're saying give me all of the fields of the range table that I've specified. And it's basically expanding that out. So it's trying to tie together column references to actual table names in SQL terms. But we don't call them that. We actually call them vars. And the var is the column name, and the range table is the table name itself. Yeah.
So how is that talk about the optimizer? So the join tables are different from the range table.
So the question is, so is the join table different than the range table? Effectively, there's two pieces, okay? So the range table is just the actual representation for a data source, okay, with no restrictions on it. So again, if we have a query that has 3 tables in the from clause, we're going to have 3 range tables, okay? The joins themselves are represented separately. So as you can see here, you've got the range table, which is a list of tables that are referenced in the query. And then down here, we have the join rel list, where we basically identifies where how we're joining those together. And we have, we'll have something like range table 3, column 2 equals range table 1, column 1, right? And that's how the optimizer kind of works with it, because it doesn't really know the names of the tables or anything. It just knows, okay, I got these 3 range tables, I got to bring them together, and the join rel list effectively tells me how they fit together. And the optimizer, when it works, actually is going and it's comparing this number to this and this to that, and then it's figuring out what indexes exist on range table 1, column 2, and what indexes exist on the other side of that join. And can I use those together to do a nested loop, or can I do this join together to do a merge join? And that's kind of how it references them.
Just one last question.
Yeah.
So
the question is, if you had a subquery, how would that be referenced? And actually, what I think we do, and I haven't looked at it recently, I actually did the original subquery work, but we've kind of changed it over time. But effectively what happens is that in a subquery in the where clause, for example, what happens is you get a range table that's not joined, and that range table represents all of the tables, but they're not joined to the main table. They're actually just referenced by the where clause. So effectively with, I'm trying to think I have an example. Oh yeah, here it is. So you see this var level sup. I don't know why I know why I came up with that name, because it's, I don't know why I called it sup. I can't remember. Right, so it's basically var levels up. It's not sub, it's var levels up. And effectively, it's basically saying, for this variable, how high am I, or how low am I in the query to kind of reference it. So, for example, the classic case is a case where we have a correlated subquery. That's the classic case, where you actually correlate subqueries when you reference an outer variable inside your subquery. So obviously in that case, we can't have the subquery in isolation. The subquery actually has to be tied to the main table. So when we have a var that's referenced in, if we have var levels up to be 1, that means that that variable is not really represented within this query, but actually is represented at a level 1 up or 2 up from the query I'm in, and that controls how that actual query gets executed. So it does get pretty complicated, and I'm telling you range tables are this pretty simple thing, but effectively they could be a whole bunch of other things that gets really complicated. Yes, sir? So do rules rewrite the structure? Absolutely. The rule system is designed to take this and change it. Right. Yes, because so the question is, can range table entries be synthetic? So if in the from clause you do a select, which you can do, you can say select table A, comma, paren, select star from whatever as new table. So that would be a synthetic from clause, right? And that would be a separate range table entry, because the columns that are represented in that synthetic from clause actually have to be represented, because we may reference those in other parts of the query. So when I say select column name, that column name has got to reference a range table. So if I say select first name, okay, first name can't just be floating out in the air. It's got to be tied down, and then I've got to say range table 6, column 2, that's that first column I want to return. Because the system doesn't really want or need to worry about names of things. All that gets really washed away in the parser. And you really never deal with the names after that. The whole idea of the parser is to basically boil everything down to an arranged table and vars that reference those range tables. And then and the optimizer and the rewriter are all working in that level. And in fact, if you look at the rewriter and you look at internally what the rewriter, when you have a view, it kind of digests it down. And if you look at it, you can actually see, I think, in the system tables, the vars and the range table kind of parts, because when we're rewriting, we're basically taking one query kind of rewriter thing, and we're kind of merging it in and kind of mapping some things to other things. And it all has to be done in this way. Yeah, sure. I think that's another reason why I think in a lot of cases in your rewriter, you can rename columns and it still works, because it's all mapped it's all mapped in a lot of sense to the vars and the range table. It's not actually the names in a lot of cases. So it gets a little weird, but there's some cases where you can rename something that the view still works, because we're not referencing the names. We're referencing the offsets as they exist in the table. Now, if you start dropping columns, things start to go a little wacky, because then we can't reference stuff that used to be there. Yes, sir? So if you wanted to write a new query language, where would you kind of plug it in? Would you output SQL and then pass it in? That would certainly be the easiest approach. The hard approach would effectively be to modify the Postgres grammar, okay? And if you could modify the Postgres grammar where you still filled in the right fields, right, it would work. I know it sounds kind of funky, but there are some like offshoots of Postgres which when they want to add new commands or they want to add new functionality, instead of taking SQL, because if you have to take a language and output SQL, that language has to do a whole bunch of work. It's got to parse and it's got to know what all the column names are and there's a lot of stuff there. So a lot of people, if they're trying to implement a new language or adding to the SQL language, actually just modify the gram.y file and add new commands or add new clauses to existing commands. And as long as the structures that they're filling in come out the way they should with a normal SQL, it would actually work just fine. Yeah. I'm sorry, question in the back? No. No. Okay. Other questions?
Does the user-created functions, for example, or they don't go to this parser?
So a user-created function would actually, question is a user-created function go through the parser? User-created function is going to go through a parser that is specific to the function language that you're using. So if it's PGConf, there's a separate PGConf grammar that function has to go through. However, if the PGConf function has SQL within it, we can actually, in some cases, test the SQL to make sure it's valid. Okay, so most languages can't do that. So if you do Perl, it's going to just assume it's Perl. And whatever SQL you have in there, it better work because you're not going to, when you define the function, we're not going to check that. In PGSQL, we can do some sanity checking of the SQL that's embedded in the PGSQL because effectively PGSQL has SQL sort of as a subset of its own language. And in fact, there's a special clause that says check SQL something. So the answer is that normal languages go through their own parser, but there are some cases where if you're using embedded SQL in PGSQL, we'll even run some of that through here to see if it compiles, if we don't throw an error. Yeah. We'll probably run it through the parser and just throw it away. I know it's sad, but you can kind of see how that would work. You'd run through the parser, did I get any errors? No, okay, I'm good, right? And then you just say that function's going to be good, and then when they finally execute it, it's going to go through the whole cycle, but you've done a sanity check on it. Other questions? Yes, sir. I'm sorry? Okay, so which of these pieces take the most time? Usually the parser takes, I don't know, I'm going to say like 0.5%, 0.1%, really small. And if parsing is a significant overhead, particularly if something like an insert, where you're really not doing a whole lot of other work, you're just inserting, a lot of times prepared queries help you here. So a prepared query avoids this because it pre-parses the insert, and then you just supply the constants. You can also obviously prepare select and prepare, and if you do that, you avoid all the overhead of the optimizer, because normally when you prepare, if you prepare a statement and you run it a couple times, the system will start not optimizing anymore and will just reuse the plan that the optimizer had come up with previously. There's actually a whole bunch of heuristics where when we have a parsed plan, we'll actually run it for 5 times and we'll look at the output of the optimizer, and if the optimizer pretty much gives the same plan for the first 5 constants that you give us when you run it, then we'll be like, okay, we're probably good with a generic plan. We're just going to use that all the time. So there's actually some you can now see how that would work. There's a whole bunch of heuristics that you can use to sort of short circuit some of this. Probably prepared queries is probably the biggest one that avoids the parsing, and again, after the 5th run, normally avoids the optimization as well and the rewriter. So now you're really just going right into the executor, right? But in most cases, even aside from prepared plans, 95% of your time is in the executor. Very rarely do you see any of these others come anywhere above a single digit, a 1% number. Other questions? Good question, though. Yes, sir. So how a range table is used in inserts. In an insert, the table that's being inserted into is a range table. So you know how you say insert into table and then you specify the column names? Well, those are vars, right? So that's like, you don't have to supply the column names, but if you do, we're going to say, okay, the first value we supplied is range table 1 var 3, and the second one is var offset 4, and so forth. And that's how we kind of key up the column names you specified in the parens with the actual constant that you supplied. If you don't use a range of constants, we're still going to create a var, but we effectively just expand the whole thing, and we're like, you better give us the same number of constants as we have columns or vars in our range table.
So when you have an insertable view,
Yeah.
does Postgres have like 2 range tables and then like punches through the top of it?
So if you have an insertable view, how does that work? So effectively what happens is that the view is its own var. Okay? So the view actually becomes a var, the view becomes a range table. View is a range table, and again, you can name your view columns whatever you want. So if you mention those in the query, they better match the range table for the view you've defined. Okay? And then what happens is the whole query structure gets filled out. The parser thinks the view is a real table. It doesn't know. It just knows it's a range table, and it knows it has certain vars. Okay? In fact, if you look at the range table, you can see like some of these are filled in, but they don't have to all be filled in. They may not be filled in. And obviously, here's an example. Here's where we put the subquery for the range table. Okay? So in this case, actually, I take that back. Views have rel IDs. So view has a rel ID. It's defined in PG class. So that would definitely be there. The rel name would be the view name. The type would be range table. And then if you have an alias or if you have some checks in there, there's a whole bunch of stuff you can do. But effectively, you have a range table, and then you have the vars that go with your query. And then what happens is that query structure gets passed to the rewriter, and the rewriter wipes out the view and substitutes the underlying tables. Okay? And that rewrite is what gets passed to the optimizer. And the optimizer doesn't see the view, it's optimizing the whole thing. And the reason we have to do that is because if you join a view and a real table together, we have to be able to cross, when we optimize it, if there's 2 tables in the view and 1 real table, we really want to look at that as 3 tables. We don't want that view to be an opaque thing we can't get inside, because if we can't get inside it, we can't optimize it. Because if there's 2 tables in the view and 1 table, I may want to join the real table to one of the tables in the view, and then join that one to the other one. If I can't see inside the view, I have to join to this amorphous thing. So if you look at some other systems have problems optimizing views. We don't, because by the time the view gets through the rewriter, it's been wiped away. And you get a fresh optimization of the underlying tables, and the view has disappeared, because now that view is not a black box. We can join and use whatever indexes we want and whatever, because we see the underlying data by the time we get to the optimizer. That's why we have to do the rewriting before we get to the optimizer.
So I have a couple more maybe weird questions.
Okay.
So we have a column that is itself a row.
Yeah, okay.
Is this a range table?
So if you have a column that itself is a row, is that a range table? I don't remember how we do. What you're talking about is a row result is basically like a complex type. So it appears as though, I don't think that's a range table. No, because you can't join into that in the same way. It's basically just a field. It isn't really a result that has indexes and has a storage. It's basically a field. So we can't really optimize into that complex type in the same way we would do. So I think we just carry it around. I don't think we do anything with it. I think it just gets output. And you can test inside of it, but you can't really optimize it. It's not really a result set that I can independently scroll through. It's tied to whatever row it's stored in. So I don't think it's a range table. I might be wrong, but I don't think it is. Right. So a function, you have a function that, okay, so I'm sorry, you have a function that returns a result, and inside the function is a where clause? Right. Right. Right, so the problem is that a where clause inside a function, whatever language you're using, is effectively opaque to the optimizer. So we don't know, that whole query is going to be run independently of the rest of the system because it's basically a black box of results. Yes. Yes. The only case that the only case where we could actually not do that is an SQL function. We have the ability for SQL functions to inline those functions. But in the question, I'm sure you repeated, was if you have a where clause in a function, can you merge it in? No, an SQL function, you can actually do that because it inlines the SQL. But in every other language, it's just an opaque box. It doesn't know. For the function. Yeah. No. And that's why it's hard to optimize them, and there's a whole bunch of problems with it, yeah. Other questions? Let me go back to where I was. Okay. So this is the output, basically written a little differently, where we actually have the query structure, and you can just basically see it all kind of filled in. Okay. So any questions before we get to the optimizer? Again, I promised that I have a separate talk just on the optimizer, so if you want, I can kind of go through this a little quicker, and then we can go to the optimizer talk like as a whole separately, but I want to tie it into some of the stuff we've been talking about. But we will be coming back to this as we get into the optimizer. Actually, we're very good with time. We're only an hour, 7 minutes in, so I think we're making really good time, even though we're getting a lot of good questions. So that's good. Again, it's a tutorial, so we want to get that interaction. We want people to be asking stuff, and I think it's very interesting. So any questions before we move on? Yes, ma'am. Oh, I'm sorry. So your question is, if I'm using prepared statements to do inserts, when should I be switching to use copy?
Or what is the benefit of copy?
What is the benefit of copy in and of itself if I can do? So in almost every case, copy is going to be faster for a couple of reasons. First, there's a lot of optimizations that allow you to bypass a lot of the parsing, because if you think of the way the copy file is, it's just like tab delimited or whatever, CSV. There's not a whole lot of processing in there, right? And if you're inserting 100 rows, let's just say for small, right? All you're doing is you're just parsing the row with the delimiters, right? You're not scanning, you're not grammar parsing, you're not creating range table entry for every insert, right? There's a whole host of stuff that's going on. All you're really doing with a copy is you're just like, take the thing, get my delimiters, separate them out, and then just create a row for me and just throw it into the table. That's like it's just basically pulling rows out and then throwing them into the table. In fact, the way we do the indexes is we have like an optimization, so we batch the inserts of the indexes, so we don't sort of create a page and then add every row. We kind of create whole pages at a time for indexes. So there's a whole bunch of optimizations that go into insert. When you realize this is the work I've just done to get to the parser, right? You can imagine how much work really is required for an insert. So there's really no case where an insert, I would almost believe a single row copy would be faster than an insert. I would put my money that if you ran them up against each other, a single row copy would probably be faster than a single row insert. And obviously, the more rows you insert, the more rows that are involved, the faster the copy is going to be. So if you can get your data in copy format, I can't imagine any value to doing insert. I think that the value of doing insert is the ability to get defaults, the ability to specify only certain columns, the ability to to do a select, insert into select, right, where you're pulling data from one source and loading it in to another. Those would be really your cases where insert makes sense. But for bulk loading, I think copy is always going to be a win. I'm sorry?
Should the table be offline when I do a copy?
Should the table be offline when you do a copy? No, the table is never offline for a copy. So the question is, how does Postgres manage the log? So effectively what happens with copy and pretty much every operation in Postgres is that the rows are inserted, but they're inserted with a transaction ID which is not visible to anybody. So the rows are going in, hundreds of rows, thousands of rows, but nobody sees them. Once the commit happens, then the next transaction that gets a new snapshot would then see those rows instantaneously appear. Yeah. Yeah, so MVCC follows, copy, yes. 15 times faster, yeah. So copies 15 times faster. That's probably true in almost every case, yeah. And there's some gotcha. I mean, so the question is, is it worth the effort to get stuff into copy format? I mean, there's some argument that you have to be a naive implementation of creating a copy file is a dangerous thing, right? So you have to be very careful of embedded new lines in your code, of embedded delimiters in your code. I would effectively \escape anything that isn't ASCII, right? Or anything that isn't printable, like a new line. So there is some kind of overhead that you have to go into to get it into a format that's going to reliably load in. You have to have a special \N for nulls, for example. So it's if it's a one-off case or you're not doing it a lot, it's hard to argue that just using insert's the better way to go. It's really a question of what your speed requirements are, how often you're doing it, and whether you're willing to invest the time to create a bulletproof copy. Because if it works only 99% of the time, then forget it, right? So you really have to understand the intricacies of what could possibly throw off the copy. And usually it's pretty well documented, but again, you have to be clear of what you're doing. And insert doesn't have that problem. You can have embedded new lines, and null is a null. You just put the word null. You can skip columns. There's a whole bunch of cool stuff you can do that makes the user experience better to use an insert. Other questions? So let's go into the optimizer. And again, I'm just going to give it to you at a kind of high level here. Basically, the optimizer, and then going back, remember we had parsing and optimizing. We're skipping the rewriter. We talked about that in good detail in relation to the view question. The optimizer really has to decide three things. It has to decide, it has to decide scan method, join method, and join order. These are the three kind of decisions it has to make. The first one, scan method, do we want to do a sequential scan of the table, meaning read the whole thing? Do we want to do an index scan, or do we want to do a bitmap index scan? And again, I have a really good presentation that describes this, so I'm going to come back to that, but I'm going to give you the high level here. This is a sequential scan, very easy to understand. This is an index scan of a B tree. Again, very traditional kind of a lookup there. And this is a bitmap scan, a little different than the other two, because effectively it's normally used if you've got multiple hits. You're creating a bitmap of possible matches, and then you are effectively using that bitmap to look up in the table. Okay, so it's kind of in between the two. Sequential scan is great if you're accessing most of the table. Sequential scan's the fastest, right? If you're accessing just one row in a big table, index lookup is the fastest, okay? And sort of in the middle is that bitmap scan where you're not indexing most of the table, you're not indexing just one row. There's like probably 20 rows or 50 rows or 1% of the table or half of a percent of the table that I want to access. And the way we do this is we create a bitmap of all the potential matches, and then we run through the bitmap in an efficient manner. It also allows us to join two bitmaps together. Again, if you want to use two indexes in the same query, you can't do that here, okay? Because an index is effectively points to the heap. So what we do is we create two bitmaps using the two indexes, and we join them together. And again, very good for data warehousing type of cases. And then you use that to look up the rows. Okay. Join methods, this is the second one. Again, we'll be covering this in more detail. So the first one is a nested loop join. This is the compare everything to everything else option, right? Really good for very small tables, but it's obviously very naive for very big tables. But you just compare everything to everything else. But of course, if you have a 1,000,000 row table on one side, a 1,000,000 row table on the other side, you're looking at 1,000,000,000,000 comparisons. Maybe don't want to go there, okay? The second one is a little optimized from that. If you've got an index on one of the sides, you can actually do what's called a nested loop with an inner index scan. And of course, here, you're not comparing every row to every other row. You're just comparing each row to its index matches. Third one, this is the most popular, the one you see the most. It's a hash join. And a hash join is where you're basically taking one row and you're hashing it. And then you're taking the other side, you're doing hash lookups, okay? And then finally, a merge join is when you're sorting both sides, and then you're basically doing a lockstep. So you're comparing this to this, this to this. Oh, this doesn't match. Okay, I'm going to start here, but I don't have to start at the beginning anymore. I can start where I stopped because this is all sorted, okay? Okay, match, match. Ooh, it doesn't match. Okay, here, again, I don't have to start at the top. So I'm now going lockstep. This is really good if the two tables are really big, but you got to sort both sides. Okay. And here's an example of some of the internals we use. There's a path structure which represents the various ways of getting at your data, including the costs associated with that. We also have a path key item. We have a rel opt info. Again, a lot of very exotic sounding functions or structures in the optimizer. But effectively, if you take this simple case, 3 tables joined together with the join, you can see here some potential ways that this is optimized. Here's a hash join with a nested loop. So it's effectively here's a hash join and 2 sequential scans of joining tables 2 and 3. Here's a nested loop of 2 and 3. Here's a nested loop with 2 index scans of 2 and 3. And again, we have the cheapest startup and total. And then how can we join 1 and 2? Same type of thing. And then finally joining 3, 2, and 1. And you can see basically all the options and what it determined to be the cheapest way of going at it. One was a merge join with a nested loop. The second one was a hash join with another hash join underneath it. Okay. Again, we're going to come back to this, but you kind of get the idea of sort of what that optimizer is doing. It's basically taking the query structure that we passed, and it's basically saying, what are all the possible ways I could do it? Index scan, bitmap scan, sequential scan. How can I do my joins? Merge join, hash join. Give me a cost of all these, and then find out which one's cheapest. And that's what comes out of the optimizer. We generate a plan goes into the executor, and we're effectively done at that point. Okay? Again, I'm going to go back to this after the break, but any questions? Yes, sir.
Are there times where you spend more time optimizing the executing query?
So the question is, are there times when you spend more time optimizing and executing the query? That is a great question because it traditionally happens a lot with relational systems. What you find, and it sounds kind of surprising, but when you get to perhaps 15 or 20 tables, the amount of computation necessary to find the best plan can actually exceed the execution time for the query. Forget the savings of the time. So it's really hard to explain, but if I have a query that's going to take a minute to run or 60 seconds to run, okay, and I say I can spend another 5 minutes optimizing the query and get it down to 45 seconds, you'd be like, no, don't do that, right? Don't spend 5 minutes trying to get the query execution time from 60 seconds to 45 seconds, because effectively the query execution time in total has gone from 60 seconds to 5 minutes and 45 seconds, right? That's the quandary you have. So Postgres does have a facility called the Genetic Query Optimizer. And it's enabled anytime you join more than 11 tables. And what it does is instead of exhaustively trying for every possible way to join, it kind of randomly picks a bunch. It never is going to pick the best plan, very rarely, okay? But it's going to pick one good enough in a short enough period of time that effectively it's going to be a win versus an exhaustive case. So Postgres sort of has that escape hatch. We've always had it from 96 all in order, 98 or whatever, where if you do a large number of, if you specify a range table over 11 entries, we'll do sort of a best guess plan and execute that, realizing that probably we're saving more in optimizer time than we could possibly gain by getting the best plan. And I'm not sure every other system has it, but I know that we do. And effectively, it's designed to do that. And in fact, you can turn that on and off. It's called GEQO, Genetic Query Optimizer. So in the config file, you can actually see that number 11 or 12 or whatever it is, or 10 or whatever it is. And then you can actually turn it up or down. So if you want a Genetic Query Optimizer to trigger at 8 or 15, you can actually change that. Even in your session, you don't even have to do it in the config file. Just you can actually set it to 3 and run a query and see what the Genetic Query Optimizer comes up with and whether that savings and optimization is something that's a win. Then usually you see it when you start profiling your queries and you say, oh, I got this query, it looks pretty simple, but it's taking a huge amount of time to optimize. That's the time when you might want to start saying, before I run that query, I'm going to set the Genetic Query Optimizer really low to enable it and then run it and see if I get a win out of it. Yeah, it's designed to hopefully work without you having to do that. But if you ever found that it took a long time, that would be the way around it. So does Postgres have a facility to reuse plans in a single session? Yes, it would be a prepare statement, and you would name the prepared statement, or you can make it anonymous, either one, and then you can re-execute it by just saying. So you say prepare, and then you say execute, and then you just give the parameters. And it would automatically execute the query for you. Yeah. Other questions? OK. This is the thing that comes out of the optimizer, the plan. So this is that thing that basically describes what goes into the executor. So this is effectively a recipe or a mini program that tells the executor what to do. And all the executor does, it takes this plan and just runs it. It's just like a state machine. It's like, oh, you want me to do a sort? Oh, you want me to do a merge join? OK, I'm going to do that. You want me to do a sequential scan? You want me to do an index scan? You want me to create a bitmap? I'm going to do whatever you tell me to do, and it just runs that. OK? And this is what it kind of looks like if you kind of spread it out. And effectively, this is the end. So we've now gotten to the end where we're actually returning that one row that we started an hour and 23 minutes ago talking about. We've walked through the whole libpq network, parsing, optimizing, plan, executor thing. And we have our one row out. OK? And this is kind of proof, if you're curious exactly how long it takes to run through these sections. There's some variables in the PostgreSQL file, which again you can put in your single session. It's like log stats. So you can actually log how long the parsing takes, how long the rewriter takes, how long the optimizer planner takes, how long the executor takes. And you can actually see. So for example, what it's showing here is it's saying the parser, which is just the grammar, just the tokenization, tells me how many seconds it took, fractions of a second, how long parse analysis took, how long the rewriter took, how long the planner took, that's the optimizer, and how long the executor took. And here's a good example. This is 0.01 seconds, and this is 0.04 seconds. So again, even for that simple query, it took 0.01 seconds to optimize it and then 0.04 to execute it. Okay, so 25% or 20% was the optimizer in this very simple case. Okay. This is the flowchart chart that I promised for you. And I think it does a good job of sort of summarizing what we've talked about. So it's basically the same kind of flow that we saw in the previous example, except it actually has the C function names that the backend uses to actually do these things. Okay? So we start down here in yellow in libpq. We go up and around, and we end up back here in libpq. So effectively, we have a query select star from PG class. It goes into a PG send query, and I'm going to show you the URL for in a minute if you can't read it. Put message, and then we basically, here's the init message start. Here's the little Q command. Remember I showed you the protocol. It had a little Q at the beginning. So it sends the Q. The backend identifies the Q, runs something called exec simple query. The scanner breaks it up into tokens. It then outputs something called a select statement. It goes into analyze rewrite, which basically creates a query structure. It goes into the optimizer, which then plans it. It generates a plan. It goes to the executor. It runs all this. Then it sends the result back to, and in fact, it looks like the D command is this thing that says you're sending something back. So the URL for this is actually here. I know it's a little hard to read. Let me see what I can, actually, let me back up here. So there's actually a blog entry that has this detail in it, so I'll show you that. So that's the blog right there. Let me see if I can, so March 11, 2009. On my website, under my Postgres blog, it's called Query Source Code Flow Diagram Completed. And it's basically that chart I just showed you. Okay? So just another way of looking at it. You can actually look at one of the functions I've named in there. You can actually see what the code is doing. Okay? Any questions?
On the optimizer, is there a plugin that I can basically extend?
So is there a way of plugging into the optimizer? Yes, there's something called hooks, which allow you to call in the optimizer. For example, PG shard by Citus Data actually is implemented using optimizer hooks and executor hooks. So you can actually sort of short circuit the optimizer, go out, do something, and then come back and continue. Yeah. Other questions? Okay. So back to the slide again. We're gonna go through this slide deck real fast, and then move into the next one. So just to kind of wrap up this slide deck, some of the internal stuff, as you may know, Postgres is made up of 8K pages. So everything's stored in 8K segments. An individual page has a header and a number of item pointers. And then they have rows, which we're going to label tuples here, which start from the back and move to the middle. So when the item pointer runs into the tuple, the page is full. We have to go to create a new page. Okay? This is what the header looks like for a row. Whole bunch of information, and I'm going to be able to cover this if we get to the MVCC talk, which talks about the visibility information and the transactions that created or deleted these rows. And that's very important in how Postgres does concurrency and does ACID compliance. And again, a whole bunch of other sort of housekeeping stuff on top of there. This is what the index structure looks like. We technically have an internal page, which has ranges of values, and then we have leaf pages, which actually have matches or keys. And then obviously those point to specific rows that exist in the database. This is what an index row header looks like, obviously much shorter than a row header. We support a whole bunch of different access methods. In fact, this is not complete. We have GIN and GIST and SPGIST. Again, very pluggable system. We have something called the transaction status log. If you've ever seen PGC log before, that's what it is. It basically represents the transaction commit information. So for example, this transaction right here, there's 2 bits per byte. So this is transaction number, let's see, 18. and it has a status of 00, which means it's in progress. Transaction 19 is 10, that means committed. Transaction 2 is actually aborted because it's 01. So you kind of get an idea that the row itself has transaction IDs on it, but it's actually the C log which tells the system whether that transaction was committed, aborted, or is in progress. And this is one of the things that we keep in shared memory because, of course, when I mark a row as committed or when I mark a transaction as committed, everyone needs to see that right away. So that's a shared state. Okay. In fact, when Postgres commits a transaction, technically all it does is set the bit here to committed. Because it's already added all the rows or deleted all the rows or whatever it's going to do, but those changes don't become permanent until we mark that as committed. And then everyone sees those deletes or sees the inserts. This is the same issue with copy. The rows are copied live, but they only become visible when we've marked that as committed, and because that's in shared memory, everyone sees the change right away. It's kind of a weird design, but it actually works really well. Questions? Yeah. Okay, so the question is, this structure has a limit of 32 transactions. That's right. So the real structure is the C log. I think all the files are 16 kilobytes. So each file represents, I guess, 64,000 transactions. And then you can have multiple of these files in the C log directory. So effectively, you can have status for millions of transactions. And of course, Postgres doesn't really you can't really get rid of it until you do a vacuum freeze, and that happens probably potentially every 2 billion transactions. So you could have a whole bunch of these files in there. But again, because it's only 2 bits per transaction, it's not a huge amount of storage. Next question, yeah.
How are the Xmin and Xmax used? Because transactions should be the leaf, right? You get transaction isolation. You can't just look at am I in the range of, the soup was alive.
So how are the Xmin and Xmax used? That's actually related to the MVCC talk I can show you. I actually have the heuristics of what a snapshot looks like, because you're right, you can't just look at a range. You actually have to record the current transaction counter and all of the running transactions at the time I took my snapshot. And therefore, you have sort of a range with holes in it for the transactions that are currently still running. It's effectively the way we do it. Other questions?
What is confirmed written to disk?
What is confirmed written to disk? So confirmed written to disk is actually not this. Confirmed written to disk is the X log. So when you commit a transaction, you're actually writing a commit record for that transaction ID to the X log. The X log is is written to the kernel and then f-synced to durable storage. And that effectively is what this is another representation of that. But the durability is actually not this file. We're not f-syncing this file on every commit. We're merely f-syncing the write-ahead log, which is, again, the traditional way that most systems do that. Other questions? Okay. So again, this is sort of the logic of how we do it, but I'm going to show you this. I'll show you this MVCC in a more detailed thing later on, so I'm not going to cover that now. Again, I'll show you those in a minute. This is the snapshot structure, which allows us to record a snapshot. We have a proc structure. Basically, every session is a proc. So we record things like, what semaphores is it waiting on? What locks does it held? What's its process ID? These type of things. We also have, obviously, in a bunch of lock modes. I have a separate lock talk that nobody's really asked about, so I'm probably not going to cover it today. This is sort of how the locks kind of work within shared memory. It's pretty complicated. And this is kind of the system tables of how Postgres kind of ties everything together, how we do things like plugins for index methods and stored procedure languages and data types and things. Because everything's recorded in the system catalogs, therefore, it all kind of works together. I am giving a talk tomorrow called Postgres at the Center of Your Dataverse, which covers some of this object relational catalog stuff. So if you're interested, you might want to catch that. Again, the ability to create a whole bunch of different things in Postgres. We have caches for a whole bunch of things, relation cache, system cache, file descriptor cache. We have a proc structure, lock structure, buffer. These are all things in shared memory. I'm going to show you that in a minute. Shared buffers, again, something that's pretty key. This is the sort of structure we use to manage shared buffers. But again, I'll talk about that more when we talk about shared memory. And we have some memory routines and so forth. Okay. So that ends sort of the intro. I think we had interest in two particular areas and perhaps a third. The first one was there was interested in the shared memory presentation, where we actually explain what's in shared memory, how it's used, how we set locks. The second one I think we're interested in is the optimizer, talk about the optimizer. I think those are two good ones. If we have time, we'll also look at the MVCC one, if that works for everyone. Is there any other topics that people were like, oh, I really wanted to know about? Because I probably have a slide on it, but I need to know. The buffer cache. So the buffer cache, the shared buffer cache is something we're going to talk about when we talk about shared memory. Yeah. Okay. So let's, we're gonna hop out. Let me get out of the full screen mode here. Sorry. There we go. I'm sorry, I'm hitting the wrong button here. So leave presentation. I thought one of these buttons got me out of this, but it's not working. So let me do this. Close that. There we go. Okay. Somebody asked a question during the break. Is there a way to see if GEQ, if the genetic query optimizer is being used? I wasn't quite sure the answer, so I got onto the Postgres IRC channel and actually asked the question. The question was, is there a way to see if GEQ is being used for a query? In general, does explain show it? The answer is not without splitting it into two columns. It says explain does not show it. So there's actually no good way to see if the genetic query optimizer is being used. Maybe that's something we need to get fixed, because there should be a way of seeing it, but right now there isn't. So that was a good question, I thought. And a good example how when I don't know something, I ask. So the IRC channel is actually really, really helpful. We'll say thank you. And we will go offline so nobody else says anything to us. OK. So let's look at, let's see here. We're just going to check something here. Okay. I'm going to show you a different slide because I think it's kind of useful. I'm going to pull it off of I have a performance talk, so I'm just going to pull it up. But it's in a lot of the slide decks, so we'll just take a look at it real fast here. OK. So somebody asked about the shared buffer cache, and this is not a question somebody asked right away, but this is a pretty holistic slide. Because what it shows is a couple things. It shows what's the shared buffer cache do, what does the write-ahead log do, what happens during crash recovery, okay, and what is a checkpoint. So those are like pretty fundamental things. You hear these terms a lot, but you're like what is it? All right. Now nobody asked this specific question, but I think this slide kind of gives me a good way of presenting that to you. How many of you have seen this slide before? Okay, one. Okay, all right. So that's good. So let's walk through this, because I think it's hard to understand the internals of Postgres. And the person who asked about shared buffer cache, I think this is really going to give you a good explanation of that before we get into the shared memory part overall. So what we have here is we have three Postgres sessions running. So we have 3 sessions kind of currently running. And we have the shared buffer cache, which is in red, okay? And every time one of these sessions at the top needs to read or write some data, it has to do it through the shared buffer cache, okay? So why does it have to do that? Well, if I read some data and I read it into my process, other people can't see what I read. And if I change it, they can't see what I changed. So effectively, if I'm going to modify files that other people are going to play with, I got to do it in the shared area. And that's why we have the majority of the shared memory allocated to Postgres is this shared buffer cache. So all of the reads and all of the writes have to happen in that shared memory. They really can't happen in your local memory. Again, this is back to what I talked about before. We separated out the part we needed to share and the part we could keep local. So if a backend needs some data, it's going to look to see if it's in the shared buffer cache. If it is, it can start to use it right away. If it's not in the shared buffer cache, it's going to ask the kernel. If the kernel has the page, it can transfer it into the shared buffer cache very quickly. If the kernel doesn't have it, it will then go down to the disk, maybe the SSD, magnetic, whatever, Fusion IO, then transfer it into the kernel, and then kernel will transfer it into the shared buffer cache, okay? Which I can then have the session either read or modify that page, okay? So that's pretty straightforward. Is that good with everybody? Okay. Now, the problem is durability, and this actually came up a couple minutes ago. The problem is that we're modifying stuff in here, but we're not necessarily writing it to disk every time we modify it. In fact, imagine you modify a whole bunch of pages and you have to write all these pages to disk every time you commit a transaction. Obviously, the performance would be terrible. So the way we get around that, and the way that all relational databases typically get around this, is with something called the write-ahead log or transaction log, or whatever you want to call it. And what you're going to notice is that every session, every one of these sessions that has a read-write arrow going to shared buffers also has a write arrow that goes to the write-ahead log. Okay? So this one has a write arrow, this one has a write arrow, this one has a write arrow. Effectively, any time a session modifies something here, it writes it to the write-ahead log. And this write-ahead log is basically append only. You're always adding to it, you're always adding to it. All these sessions concurrently adding to it. Okay? When you commit a transaction, we force that write-ahead log down to the kernel, and we issue an fsync to make sure it gets to durable storage. Now, whether that durable storage is a battery or a capacitor on an SSD, whether it's a battery on a RAID controller, whether it's a magnetic disk that we have to wait to spin around, it has to go to a durable storage or we aren't an ACID-compliant database. Okay? And the reason we do a write-ahead log that's append only is the hope that at least we're only going to be appending like to one file instead of trying to hit like 10 files at once, which would be horrendous for performance. Okay? So this write-ahead log effectively is sort of a collector of all the changes. This write-ahead log is used for crash recovery. This write-ahead log is used for point-in-time recovery. This write-ahead log is used for replication. So that write-ahead log, which effectively only is really designed for durability crash recovery, has been extended to do point-in-time recovery, to do replication. And it does it very well because it's basically a collection of all the changes in a very efficient binary format. Okay? If your server crashes, when it starts up, it goes into recovery mode. What is recovery mode? When the server starts up, it looks at the write-ahead log. It looks at the end of the write-ahead log. It says, is there a record of a clean shutdown in the write-ahead log? If there isn't, the system assumes, oh, there's no clean shutdown, therefore the system's crashed. I'm going to go back to my last checkpoint, which I'll talk about in a minute, and I'm going to replay the transaction. So effectively, during crash recovery, you're going to replay these transactions, and then you're going to reload the shared buffer cache and then flush it down to disk, and that's how you bring your system back to consistent state, okay? Because we made all sorts of changes in the shared buffers that we didn't send to disk, but we do have a record of them all. There's a record of them all in the write-ahead log. And replaying that is effectively the way that we go through crash recovery. So if your server crashes, and if it takes perhaps 30 seconds for Postgres to start after that, that's because Postgres is replaying that write-ahead log. Now the question a lot of people ask is they're like, well, I understand that, but doesn't the write-ahead log get too big? Because you're always appending to it. When do you get rid of stuff, right? What if I have a transaction that runs for 5 days? Am I have to give 5 days of write-ahead log? No. What happens is that every couple minutes, you issue something called a checkpoint. A checkpoint effectively goes into the shared buffer cache. It finds all of the dirty pages, and it flushes them down to durable storage. Once the dirty pages have been flushed down to durable storage, we don't need the write-ahead log anymore, and we can basically recycle the write-ahead log. And this is an example of that. So here we've got dirty pages from checkpoint number 1, and the write-ahead log position's here. Then I actually am dirtying more pages, but I'm actually writing this one, for example, this dirty page got written to durable storage. Then I've written this page and this page to durable storage. And once I've written all of the pages that were dirty at checkpoint 1 time to durable storage, I can then take this page, which I'm not using anymore, and move it to the end because I don't need it. Because I've written out all my dirty pages down to durable storage. If I need to if I do need to do a replay, I don't need to go back to checkpoint 1 anymore. Now I can go from checkpoint 2 and know that all the dirty checkpoint 1 pages have been sent to durable storage.
The write-ahead log represents the query or the result?
The write-ahead log really represents neither the query nor the result. The write-ahead log really represents a file, an offset, and some bytes. So the only thing really technically in the write-ahead log is open this file, seek to this page or this offset within the file, and then write these bytes there. Because all I'm doing when I'm writing my records to the write-ahead log, all I'm doing is redoing exactly what I did in the shared buffer cache. So if I inserted a row, I actually had to write some values in particular offset within the page. And all I'm going to record here is I actually wrote a row into the page. So it's really a binary log. It's not SQL. It's not a result set. It's really just sort of I/O operations. And by replaying those I/O operations, we can basically bring the system back to a consistent state. And that's why the replay is so fast, because it's not really parsing anything. It's not doing anything. It's just opening a file, seeking, and writing bytes, and then moving to the next one. Yeah, question in the back. So each one here is whole pages, but when we write to the write-ahead log, sometimes we write full pages, sometimes we write parts of a page. So technically, the way it works, the first time we access a non-empty page after a checkpoint, we have to write the full page to the write-ahead log. From there forward, until the next checkpoint, we can write just the offsets. And the reason we have to do that is because if we don't do that, we potentially open the problem of torn pages, where part of a page gets written to storage, part of it doesn't. During crash recovery, you don't bring the system back to a consistent state. That's why we have to write the full pages. You can turn off the full pages if you want, but again, you open up to the possibility of having torn pages. So in most cases, they're really just offsets and partial pieces. But again, first access to a non-empty page would need to, by default, write the full page to the write-ahead log. Yes, sir? So you're saying the write-ahead log just has the offset and the data, but where does it get the data? The data actually, if you look at the code, in the code path where you're writing into the shared buffers, we basically just duplicate the write into the write-ahead log with some header information to tell us what to do. Like, is this a write? Is this a? And there's a little more information. I can kind of tell I can kind of tell if I'm adding a row or deleting a row. Like, there is some data in there in the header, but in most cases, that data is not really used a whole lot. We're just replaying a delete or whatever, and that delete is basically say, offset here, write these values there, and you're done. Yeah. So if you're doing an insert, that data is in the write-ahead log. If you're doing delete, really the only thing in the write-ahead log is the item ID of the row, and probably like the XI, the transaction ID that deleted the row. You wouldn't write the deleted row in the log because That's not what we do when we delete. We just mark it as deleted. And again, if we get the MVCC talk, we'll be able to show you that. Right-hand log file is a physical file. There's 16 megs in size. Yeah.
So this one is this the latest WAL file that's loaded into your memory? That's where it is.
So the wall, you really only have one active wall file at a time. Yeah, it's really the wall file that you're appending to that you care about, right? Now during replay, you might have to go backward one or two wall files to get the previous checkpoint, because you have to run from the previous checkpoint forward, because everything before that checkpoint got flushed down. So you really go backward in the wall to find the checkpoint, and then you replay forward. Yeah. No. Because you're really writing, I think the buffer size is 8K, so it's really writing little pieces of that 16 meg file. It's not writing the whole thing. You kind of got it, you have an offset of where it is, and you're just writing little appends to it all the time. But the whole 16 meg file doesn't exist in memory. There's no reason to have it, because as soon as you get it to fsync to disk, you really don't care about it anymore. The only time you care about it is in crash recovery. So it's a write-only file unless you're in crash recovery, at which point you're just reading it. It's a very, that's very efficient because you're doing the way you're doing it. You're never reading it while you're in operation. Yeah.
What is this ones and twos in this block?
I'm sorry?
So what are these ones and twos in this block?
Oh, so the ones, okay, so what are the ones and twos? The one are the pages that were dirtied at the first checkpoint, and the twos are the pages that are dirtied at the second checkpoint. Okay? So my point is, when I start checkpoint 1, I've got 3 dirty pages. As I'm running the checkpoint, the next phase is dirtying pages, but that's okay, because I only care about the ones that were dirtied at the time the checkpoint started. So I can keep dirtying pages even though I'm running a checkpoint, because the checkpoint can take 3 minutes. It does a trickle. It doesn't flush everything out at once. It kind of tries not to use too much I/O while it's working. Yeah. So the question is it flush only committed records? No. So for example, this is actually getting back to that case. If you had a 5-day transaction, okay, we're going to flush, we're going to write to wall everything that transaction does for 5 days. Okay? What we're not going to do until it's completed is to write the wall record that says that transaction ID is committed. Remember with that C log? So all the stuff we do, all the inserts, all the deletes, that stuff gets written, but it doesn't actually have any effect. Nobody sees it until we issue the commit. So that's why we can checkpoint every 5 minutes, even if a transaction is taking days or hours. Okay, so all that stuff, if you're doing, a billion inserts, the bottom line is we're gonna insert a billion rows, and if you abort, then we're just gonna clean them all up, right? But all billion rows probably are gonna be in the wall, because we had to move ahead. We couldn't just wait for your transaction to finish. So we had to record all those in case you committed right after that, and then we needed to replay it maybe in a crash. Yeah. So in a replica, okay, so the question was regarding replication. So let me just pull up a really quick slide here. Okay. So in replication, what effectively happens is this is how you set it up with where you start recording the wall, and then you do a file system backup and you restore it right away. And but this is effectively what happens in a replication setting. You have a primary which is generating write-ahead log records as the database is changing. Okay, and those are shipped over via the network to the slave, and the slave is replaying in crash recovery mode all of the activity from the master. Okay? So effectively, a slave or a standby replication mode is merely perpetually in crash recovery mode. It's merely replaying, and this is again an example of how the write-ahead log started only for crash recovery, was enhanced to do point-in-time recovery, and then became used very significantly for replication because we're now replaying everything that's happening. I mean, technically everything, when we crash, we're replaying everything that happened before the crash. Effectively, this is a little more information. It's replaying everything that's happening on the master continually. I think this is a good slide because it kind of illustrates the idea of crash recovery as being extended to do streaming replication. Yeah.
When you start up Postgres database and it's in recovery, you can't connect. But when you're running as a standby, it's perpetually in recovery, you can.
Right. So the question is, when you crash and you go into recovery, you can't connect, but you can connect when you're running in streaming replication mode. So there's a special mode called hot standby, and it allows you to do read-only connections while effectively Postgres is in crash recovery. I guess technically we could allow read-only connections during crash recovery. It would be kind of weird because people would kind of odd that they connected, but they could only do read-only queries for a while until it went into read-write mode. But foundationally, I don't think there's a reason we could not allow read-only queries during crash recovery because it's effectively doing the exact same thing. Now, there are some other things that when you're in crash, when you set the wall to hot streaming, when you set the wall to hot standby, there are some additional things in the wall which allow you to do those read-only queries. So, you could kind of, I don't know. I guess we could work on it. It might be something we could do. But right now it doesn't work that way. Yeah. Yes, sir.
Do you send to the wall or do you send read commands? I mean, if you are running in hot standby, you probably want to warm up the cache.
Okay, so the question is that write-ahead log have any kind of selects in it? No, they're only data modification commands. So in terms of the cache, what happens is that the cache on the standby is a mixture of the write transactions coming from the master and the read-only transactions that are being run on the server. Okay, that's probably the optimal layout. Now, you could argue that if you're not running read-only queries, you might want to pass some of those selects in so the cache would be hot. We've never really gotten to that level. I guess it could be an option to sort of run some of the queries to keep the cache sort of warm with the types of things that you do. It's an interesting idea. We only got the idea of warming the cache, the PG pre-warm, in the past couple of years. So this would be sort of the next level of that, where you actually ran some queries so that if you did fail over, that cache would be ready with some of the data that you use most often. It would be a cheap. So you're saying it would be a cheap implementation to do that. Yeah, it would be interesting. I would say if you're using the standby to do read-only queries, you probably don't want to do that. Because in a way, the read-only standby is going to be perfectly set up for the type of queries that it gets, right? It's going to be, but if you're doing failover, then you might want to do that. I don't know. It's an interesting question whether running them. There's no mechanism to send a query in the write-ahead log, so it would have to be some other. What's this? You don't need to send a query. Oh, so every time you read a page, you would have to, but that would be a lot of wall traffic. That would be big. So that would be a lot. You'd have your wall would be really big because every page access would all of a sudden generate, because yeah, I mean, a sequential scan might generate huge volume of wall. Yeah, I'm not sure it would be a win because you would slow down that You'd slow down the master because the master would be generating a lot more wall. So, it's interesting. I would more suspect that you'd have some kind of mechanism that periodically would throw the select queries to the standby at the same time they send to the master. Something that was external to the wall, which would kind of keep it fresh. But I haven't really thought about that. It's a good question, though. Other questions? Okay. So this is another presentation, just if you're curious, Magic of Hot Streaming Replication, again, on the same website. Let's go into shared memory, because I promised that was going to be our next thing here. And this presentation goes into a lot of detail about how the shared memory is basically laid out. It also talks about the storage format. It talks about locking. It talks about spin locks. It's kind of interesting, again, to give you a window into what's going on. So we're going to talk about the storage format, shared memory, shared buffers, row access, and locking. Okay. So many of you understand Postgres puts data into a directory, typically called data, in your file system. We don't use raw devices at all. And it has all of these sort of subdirectories, which we've talked about. PGX log we've talked about. PGC log we've talked about. The database, the directory is probably most interesting is base, because that's where your databases exist. It's called base because it's a database, right? Like, yeah, I know. This came from Berkeley, so I'm going to have to just thank them for that cuteness. Inside the base directory, we have a subdirectory for every database. The subdirectory number 1 represents template 1, and again, we have some other numbers in here. Inside the directory, we have a bunch of files. Those are either indexes or they are tables. So the only thing really stored there, indexes and pay tables, and again, some housekeeping things like visibility map and free space map. Inside the table, we have 8K pages. We've talked about this already. So I've kind of drilled down from the data directory to the base directory to the subdirectory for the database, and then to a specific table. And now we're looking inside one of those 8K pages. Okay. Inside that 8K page, you've seen this before. This is the layout of the first 8K page, which again are identical for all other 8K pages. We have item pointers, we have rows, and again, the item pointers point to the rows, pretty traditional here. Inside the page, we have tuples. Tuples are actually rows, so an actual row, it's called a tuple. Inside the tuple, we have a header. So here we're inside the tuple. We have a header containing all this information and a whole bunch of values, which effectively are the fields or columns that go with that particular row. One of the interesting things is the way that these values get defined is actually data type specific. So for example, if you want to insert an integer, let's suppose you want to insert the integer 9241, we will take that string and we will call a function called int4in. And int4in will basically take the string, convert it to a binary that matches the CPU representation for an integer on that platform, and we will plop that in, knowing that an int4 is 4 bytes long. So again, getting back to the way we do things in a object relational system, we don't really know what an integer is. We just know that the word integer, the type integer, has an input function called int4in, and we pass a string to it, and it passes 4 bytes back to us. Okay? So you can see how you're abstracting and how new data types can be created just by creating new input functions. Kind of cool, right? Same thing with a string. If I want to output a field, and this is an example, a text field, I can call text out. And text out effectively can read that value in the row, and it effectively returns a string to me. Again, we're talking very abstract. We don't understand what a string is. We just know that this text data type has a function. You send it a pointer. It reads whatever's in that slot and then passes it back out. Okay. Any questions? Okay. This is the internal representation of what a header looks like. So this is the xmin and xmax. This is very key for transaction control of rows. I'm going to cover that if I get to MVCC. Here's the item. Here's the the structure header, the info mask. We have a bitmap of nulls here. So if there are any nulls being represented in that table, we actually have little zeros and ones to represent which fields are null. So for example, if you have a row that has a lot of nulls in it, the only overhead is 1 bit per null. Okay, so it's kind of nice. You just have a little bitmap string and identifies which of the fields are null, and they don't take any storage. So it actually is really well optimized for null storage. It's kind of nice. Yeah. So the item. Yeah, so the item, the question is, what is the item pointer pointing to? So the way the page is set up, we have potentially an index, okay? And indexes never point to the rows themselves. The index always points to the item pointer, and the item pointer points to the row. The reason for that is that if we have deletions of rows within a page, we want the ability to compress and remove rows in a page without having to touch the index. So the index up here, which is obviously very hard to get at and requires a lot of random access, points to the item pointer. If we want to move a row from here to here or here to here, we just move the row and we update the pointer here. The index never needs to change because it's pointing at that fixed item pointer. Okay? So that design came to us from Berkeley. It's worked very well. That's why the item pointers are there, to allow us to remove rows without having to effectively touch the index. Yeah, it's kind of a bad diagram. It's not pointing, because I was afraid if I pointed to that, people would be like, it's a line. Like, why are you pointing to that? So it really doesn't point to the head, but it's unclear, particularly because the rows are not really read. The rows are read this way and up. So that would have been very confusing because the head of the item pointer is here, but the next one is not here. It doesn't go this way. It goes this way and then this way, and that would have been just too much for people who normally read, that way. Yeah.
The item pointer tells you how far ahead from the beginning of the 8K block to read.
The item pointer, yes, tells you how, it's like the offset of that particular page. And I think it's only, I want to say, is it 6 bits? It's very, or is it 6 bytes? It's very small. The item pointer is, because you only really need to know the offset that goes to 8K. So I'm trying to remember, 2 to the 8th is 256, so I guess it must be, maybe it's 12 bytes. I think it's 12 bits, I think is what it is.
Probably smaller than 12 bits because
The header couldn't be there, yeah, I can't remember how we did it, but it's really small. So these are tiny little fields.
each tuple is a fixed length of storage.
No, the tuples are totally variable storage. I'm sorry. Total tuples are totally variable storage because you can have strings that are long, strings that are short. We have a way of, variable length fields have a header on the front, and typically the header used to be 4 bytes. Now, if it's a short string, it's only 1 byte. So we have like mega headers for long strings and 1 byte headers for short strings, and there's a whole bunch of variability going on here. Yeah.
You could have a row that's greater than 8K.
If you have a row that's greater than 8K, we have a toast table, which I have not covered, which actually stores the long values and it gets the long value out of the sequential scan, which has a lot of benefits to it. So you don't have to do a lot of the shenanigans with other systems where long rows end up being really slow. It automatically stores the long values out in a toast table, and therefore you only really get the short values in the main table. And it has a pointer that goes to the toast if you need the long value.
What is that? Is it 8K?
No, it's typically around 2K. Yeah, 1.5K, 2K, depending on how wide your row is, yeah. But there's not a really great heuristic, but usually it's around the 1.5K, yeah. Question over here. No? Yes, I'm sorry.
When it extends by 8K or?
Every time the table extends, it extends by full 8K. That's right, yeah. I'm sorry, yes?
You're saying that
That's right.
To do that for values that have like variable length, like text or long?
So the question is, if you have a long value, it stores in a separate location. Does it do it for text or blobs? Effectively, almost all of the short values, like integer, it's typically not going to store offline. So almost pretty much every one that's stored offline is going to be variable length and long. Yeah. So. So will it, well, so it's going to try and get the row, I think, to under 1.5K. So if you have a row with a lot of fields, it may start throwing even fairly short strings out into toast to get that row down to 1.5K. Yeah, so it kind of there's a whole heuristic. It'll pick the longest one first, the longest value in the row, because there's no pattern. Some rows might have a whole bunch of fields in toast, and some rows may have no fields in toast. So it's not something that happens at the column level. It happens at the field level, right? So it kind of runs through, and it's like, oh, this is kind of a long row. What's my biggest field? Let's throw that to toast. OK, now how big is it? Oh, it's still too big. Oh, let's do another one. And it kind of runs through until it gets it down to sort of where it wants you to be, if that makes any sense. Other questions? OK. Everyone's good? OK, so let's talk about shared memory from an abstract point. This slide has a lot of information in it, as you can imagine. So I talked before about the idea of Postgres being process-based, and this kind of drives that home. OK, so if you look at the process to the far left, you'll see that that's actually labeled as the postmaster. OK, that's the thing I talked about earlier, where I have the listener, the one that accepts connections from the port, does some level of authentication, and then creates a sub-process to handle that session. Okay, so when the postmaster starts, it basically starts up a binary, it allocates some data, it allocates some stack, but most importantly, it allocates a shared memory region. And every child of that postmaster is going to inherit that same shared memory region. Okay? So when you create a new process, when you create a new session in Postgres, all we're really doing at the Unix level, on Unix, not on Windows, but on Unix, is all we're really doing is we're calling the fork system call. I'm not sure how many of you are operating system people, but effectively the fork system call takes an existing process, makes a copy of it. Okay? You're using the same program text because you're running the same program. Okay? You're getting a copy on write copy of the data segment and the stack. Okay? And you're inheriting any sockets and shared memory. Okay? So what happens effectively is that the new child has the same, or is running the same program, already has the stack set up, already has the shared memory set up, and all they really do is to allocate their own data and additional stack calls. Okay? If they modify any data in the data segment, they're automatically going to get a new copy. That's why it's called copy on write. Effectively, any data pages it inherits, if it modifies them, it gets a new copy. Okay? If it doesn't modify them, it maintains the same copy. This is why this fork thing is so efficient, because you're not really starting a new process, you're just duplicating one that's already running. Okay? And then more importantly, the shared memory is mapped in a way that if I make any changes to that, it is not copy on write. Everyone sees the change right away. Okay, so you can see how Postgres is leveraging what the Unix operating system gives us. It gives us some pages which are copy on write, which allows us to sort of preload sessions and allows the postmaster to sort of do some initialization so that each session doesn't have to do it. That's existing in this little yellow shim that we have here, okay, or roughly kind of there. And then, again, each session has its own private data space. Doesn't interfere with anyone else, but it also has a big public space, which is where we put things like the shared buffer cache, right? Because as we talked about earlier, we put the shared buffer, we have the shared buffer cache there, so that if I modify a page, somebody else can see it right away. Okay? So the majority of that shared memory is probably the shared buffer cache. There are some other things in there. We have the proc array. We talked about that. That's the we have a slot, we record for every session, what's this process ID, what locks is it holding, what user ID is it, what database is it, and so forth. We have some auto vacuum things, some background writer information there. We have some information about locking, some information about statistics and synchronized scans. We have the Xlog buffers and the CLog buffers. These are in-memory representations of the most current data we're writing into the Xlog and the CLog. Okay? We have sub-transactions, two-phase commit, multi-exact, shared validation, and we also have a buffer descriptor section. Okay? Most of the things at the top are fairly small in relation to the shared buffer cache, because shared buffer cache can be 20% of RAM, so that's going to be big, right? These other ones are fairly small. The good thing is you don't have to manage them too much. They pretty much manage themselves. There's not a whole lot you need to do. Most of them are auto-tuned, and as I mentioned before, we also have semaphores. If we need to sleep for a long period of time, we have the option of doing that with the ability to sleep on a semaphore. Any questions about that?
For example, shared buffer is 2 GB, then all the sessions will share that 2 GB.
So the question is, if you set shared buffers to 2 gigabytes, all the sessions share that 2 gigabytes. That's exactly right. This is completely different from work mem. Work mem is always allocated in this local data area. So if you set work mem to 10 megs, every session can allocate 10 megs for a sort or a hash. Okay? Shared buffers, by its definition, when you set that, that is the total for the entire cluster. Everyone will share that 2 gigabytes if you define that to be that. Okay? And again, a good example of how we've got some memory that we're sharing, right? Because we have to share. But if you're doing a sort or a hash, nobody needs to see that, right? Nobody cares what sorting you're doing. Your sorting is your sorting. It relates to your query. Nobody else needs to see your sorting. So therefore, that's done in private memory. Okay? And that's kind of hard sometimes people to get down, but the work mem and maintenance work mem compared to shared buffers is shared. Work mem, maintenance work mem are local, allocated in that yellow section. And now when you kind of see it, you're like, oh, that's the pink section, that's the yellow section, right? You can remember kind of visually where that memory is getting allocated. Other questions? Okay. It gets a little deeper. I'm going to try and tie together 2 things I've talked about already, which I think is kind of interesting. At least I found it very interesting. And that is the idea of reading from the file system and reading into shared buffers. This is kind of a little bit of a twisted thing to kind of get your head around. So down here, you probably recognize this from the earlier slides, right, where we talked about the idea that we have a data directory and a base directory, and then a directory for the subdirectory for the database and the table, okay? And when we do a read into shared buffers, all we're really doing is taking a single 8K segment or offset from that file and reading it into an 8K segment in shared buffers. There's no translation. It's just saying, pick up whatever the file system, put it right in shared memory. Okay? And we do have, so here's an example. We've got 3 8K segments here. Again, the in-memory and the on-disk are exactly the same. Same layout, same item pointers, same tuple header, same everything. It's just copied straight up. I'm not sure how many other systems do that. Well, the way Postgres does, it just comes up straight up. There's no translation. Okay? We also have a buffer descriptor area, which allows us to record who's working in individual buffers. You can pin a buffer. You can lock it if you're going to make changes to it. Again, sort of a housekeeping place for shared buffers. Okay? So let's look at an 8K page. Remember, I already clearly said that what's on disk and what's in memory is exactly the same. Here I have an 8K page, and here I'm doing a read or write to a particular page or a particular row in memory, which is, again, is the same thing as on disk. Okay? So effectively, what you're doing, and this is kind of weird, what you're doing in C when you're running through shared buffers is effectively you're just walking through the row in memory. It's an exact copy of what happens to be on disk, but it's in memory now, okay? So here's a loop called no cache get adder, and effectively what it's doing is it's saying if you're looking for a particular field number, you loop through starting at 0, and you hop through either depending on whether it's a null, whether it's a variable length, or whether it's a fixed length. So if it's integer, 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 you're jumping 4 at a time, okay? If it's float or double, you're jumping 8 bytes at a time, okay? If it's a variable length, you're reading the first byte or first 4 bytes to tell you how long it is, and then you're scanning forward depending on how large that variable field is, okay? You're just kind of walking through this, and then once you're done, you do a fetch adder, okay? And fetch add, effectively all it's doing is it's saying, if this is a 32-byte int, just return to me a pointer to that 32-byte int in memory, which happens to match exactly what's in shared buffers. If it's a 16-bit, then give me a pointer to that. If not, then give me like sort of a character pointer for a single byte. If not, just give me a generic pointer and I'll figure it out. Okay? Right, it's running through this code is looping tuple to tuple to tuple. Once you've found the tuple you want, which is what fetch at does, we basically now say, okay, now that I've found the offset in the row I want, is it a 32-bit? Convert it to an integer, right? Make it an int. Just cast it to an int. Just take the 4 bytes that happen to exist in shared memory, cast it to an int, and give me the int back. So, I'm sorry, when you use an index?
So for example, when I do an index lookup, use the item.
Okay, so when you do an index, so the question is if you do an index lookup, how does that work? The index lookup really is just getting me to the row through the item pointer. This is past that. So all the index pointer tells me, all the index does is to get me to the row I want, but now I'm working through the row itself. So that would be, I'm going through a B tree and I'm going left and right until I get to the pointer I want, and then I'm going to the row I want. Now I'm looping through to find which field I want in that row.
The fact is that I'm reading the page, I get the item pointer from the lookup, because the big header.
Right.
If item pointer offset is that's all.
Right, yeah. You're still reading an AK page, and you still have to read the item pointer. That's a good point. The index pointer is going to point to the item pointer. You read that AK page. You say, oh, I want item pointer number 2, item number pointer 2. You read on that AK page where that points to in the rest of the AK. Then you go to the rest of the AK, and you say, OK, let's start reading that row from there forward. Okay. But my point is that you're actually here just casting an int. And the same thing with int storage. If you wanted to store an int in a specific field, you just say, that's an int pointer. Just send an integer to those 4 bytes. So there's no translation really going on. What's on disk exactly matches what that CPU assumes it would look like in memory. So in a way, those AK pages are really like memory dumps. They're not sort of compressed. They have the same alignment requirements the CPU has. They're really not optimized. They're optimized for the CPU itself. And that AK page is just coming in with the exact same alignment and everything. And things like integer lookups, float lookups, you're just basically saying, at that memory location, there's a float or there's an integer. Bring that and bring it into the CPU. So it's actually really efficient how that process happens. Yeah.
Assuming that no field is so large that it has to be in a post file.
Right.
Every column or field in a row will be stored sequentially together.
That's right. So assuming there's no toast, offline storage, every field is no nulls. Every field is going to be stored sequentially next to each other. That's right.
You split a row into 2 AK blocks?
Will I split a row into AK blocks? No. I cannot split a row into 2 AK blocks. The row has got to fit in typically under 2K.
Well, what I mean is you fill the block up and the block becomes fairly full.
Right.
Do you write half of
No.
the row?
So if your page is almost full, then you're going to, and the new row won't fit in there, we're going to open it, we'll create a new page where the full row will fit. We won't try and do parts. And the reason is because actually coming back here, when I pin that row, I'm pinning the whole row. The idea of having to do 2 pins across 2 pages would be like, don't do it, right? So the data has to maintain really on one row, okay? The last thing I wanted to talk about is the way we do locks. This is kind of interesting. Effectively, we have different types of locks. We have the shortest duration lock is what we call test and set lock, or TAS, test and set lock. Then we have spin locks, and then we have long locks, long-lived locks. I'll talk about. Now, test and set lock is fortunately implemented in every CPU type that we support. So there is assembly language code in Postgres for every CPU type we support, which actually shows you, does a test and set in an atomic manner. And what effectively a test and set does is it takes 1 byte of memory and it tries to put a 1 in, and if a 0 comes out, it basically puts a number in and it brings out the number that used to be there. Okay? So when you initialize your system, you initialize it with 0. The first time a 1 comes in, a 0 comes out, oh, success, I got the lock. You can do whatever you want. Once you're finished, you put a 0 in, and you're done. Okay? If somebody else tries to come in and you already have a 1 in there, they get a 1 out, they're like, oh, that didn't work. Okay? So that's what a test and set instruction does. It effectively puts a value in, and the old value comes out. Obviously, super fast because it's assembly language, and it's one CPU instruction. Okay? And this allows us to do very high concurrency locking by effectively just trying to put a 1 in and hoping a 0 comes out, which means the lock is available to us. Okay? This is the assembly language code that we use for the Intel x86. So this is I think this is the 32-bit assembly language, but again, the 64-bit's pretty much the same. We do an optimization here where we compare to see what's in there first, to see if it's a 1 already. We don't even try. But if it isn't, we do an exchange B, which is our test and set, and then we look to see what comes out. If a 0 comes out, we're good with the lock. If not, as you imagine, the lock might fail, so we have a spin lock. A spin lock effectively says, oh, I didn't get the lock. Let me go to sleep for a while and then wake up again and try it again. That's what a spin lock does. So it's going to spin around. Every time it fails, it'll get a longer duration of sleep until it can eventually get that lock. And finally, we have something called lightweight locks. These are actually recorded in shared memory, and we actually sleep on semaphores there to allow us to go to sleep. And again, I talked about this earlier on. The semaphore can wait. When I finish with the lock, I can wake up anyone waiting on my semaphore, and they can then go to acquire the lock. Okay. So there's a lot of stuff here, a lot of obviously very low-level stuff. But it's actually really efficient when you look at the design, the way we use the fork system call, the way we set up shared memory, the way we map the 8K page from memory into disk, the way we do test and set with assembly language instructions, the way we walk through particular rows. It's actually really, really efficient and gives Postgres very good performance. Okay. The last thing I wanted to talk about was the optimizer. So I'm just going to pull that up. Any questions while we're waiting here? And the good thing is you already kind of understand the optimizer, so this won't be sort of completely brand new to you. Any questions? Yes, sir.
Shared memory is great, but if I allocate more memory to individual session, the performance will be good. So for individual session,
Yeah.
we need memory for data and other stuff. So if I increase that memory, my performance will be better. Because per session, I'm allocating more memory.
Do you mean work mem? I'm not sure what you mean by allocating more memory per session.
So when I fork,
You fork, yeah.
at that time, it must have some memory allocated to that session.
That's correct, yeah.
So if that memory is bigger, then the performance, whatever it's going to perform inside that session, it will be faster if it has more memory.
I don't even understand the question.
He's saying per process memory is increased.
It's hard to say. So the question is if you increase per process memory. So the only way you can increase per process memory is use work mem. So that allows you to increase the amount of local memory used for sorts and hashes and reduces the amount of data we have to spill to disk for those type of operations. Whether a high work mem will help you or not, it depends how often you're doing sorting and hashing. If you're not doing them at all, it's not going to help you at all, right? So we can't really just say blanket, increasing the amount of memory is going to help me. We have to say, if we're doing a lot of sorting and hashing and we're spilling to disk a lot, which you can actually log, there's a log temp file, which will show us how much. I have some blogs about it. We'll show you how much data we're spilling to disk going to sorts and hashes. If that's slowing you down, increasing work mem will help you. But if you increase work mem and you don't do those, it's not going to help you at all. Okay. So the spill to disk, does that use the same size 8K? No. It's more compact than that, yeah.
What happens when we run out of shared memory?
So what happens when we run out of shared memory? Effectively, when Postgres starts, it allocates all the shared memory it's ever going to need for however many sessions you specified, max connections. So Postgres, when it starts, it has all the memory it will need, all the shared memory it will need for every, for the maximum number of connections that you specified. You won't get to like,
Multiple of the number of connections, and there's a minimum. Couldn't the workload require more shared memory?
no, shared memory is fixed. Fixed size shared memory, never changes. Yep. There's a good reason for that.
I know it's a setting that you have to set when you.
Right. So in fact, you can't change even shared memory settings without restarting the server. So those settings are locked down. And the reason for that is we don't want Postgres falling over when it gets to a high load, which effectively happens a lot, which is a surprise. Oh, I don't have enough shared memory. Well, you said you could handle 100 connections. So Postgres does never, no matter what the load is, Postgres will never need more shared memory than it needs when it starts. No, for reliability reasons. Does it begin to thrash? So Postgres would begin to thrash not because of shared memory over allocation, but if you increase work mem too high, then you're going to have too much memory pressure, not in shared memory, but in per process memory. And that can get you in trouble. Yes. Yes, sir.
So I believe that there is a way to increase the work memory per session. So
That, absolutely. You can change work mem per session, per query, whatever. Yeah, absolutely. Yeah. And I recommend that to a lot of people. If you're running a big report, increase it just in that session, and therefore, you're not going to run 20 concurrent reports, right? And those are usually very predictable. Yes?
if your shared memory is too small, what happens is you don't hit the cache. When you need to pay, you have to read it.
Yeah, so if your shared memory is too small, then effectively you're overusing, you're not really using RAM efficiently, and you're having to do more kernel calls to get your data probably. The cool thing is that if your shared memory is small, your kernel cache is probably bigger, so you won't need to you're not necessarily having to hit the disk as much, but you're having to hit the kernel more to pull stuff into shared memory. Yeah. Yes, sir.
The data that we fetch, they come into work memory.
I'm sorry?
All the data that we fetch from this.
No, it goes into shared buffers. Yeah, it does not. Only work memory is only for sorting and hashing locally. Yeah.
Are there any drawbacks of setting a large shared memory?
So are there any drawbacks to setting a large shared memory? Yes. The problem with setting a large shared memory is you can starve the kernel for kernel buffers. So if you set a large shared memory and you dirty a lot of buffers, all of a sudden you're running a checkpoint and the kernel can't absorb all these dirty pages. So a lot of times you want to keep it in the 20%, 25% range because effectively probably most of your hot data is going to fit in there. Anything that doesn't fit is going to come up from the kernel, and the kernel can kind of get bigger or smaller depending on your memory requirements. When you set shared memory, it's fixed. So therefore, like, no matter what your requirements are, it's always going to be that size. And we've done some research, and we thought maybe you would want to make it really big, but a lot of times it makes Postgres son of volatile. It doesn't handle variable workloads as well as if you make small. There is some argument to say if you have a read-only workload and you can set shared buffers so it fits all of the data, it may be worth making it really big. But that's kind of not the typical use case, and it would be something you would be cautious about. Because again, there are some cases where making it really big would help, but you have to really understand what you're doing and make sure you measure it anytime you go beyond like that number. Yes?
Is it really, a lot of it's around the page replacement algorithm, from my understanding, with the problem of like,
So,
Other folks talking about it, right, is that that's one of the areas, like, if you actually can fit into memory from at least my performance testing I've seen, if your working set does fit into the shared buffers, and, you know, if you can still leave enough room, you can actually go much larger than 25 or 50%. The problem is if your working set's bigger than that,
right,
algorithm gets really nasty,
right.
because of how much work it has to do, right?
Yeah, so,
It's kind of non-intuitive that, like, you keep going up until you have to go dramatically down.
right. So I'm not sure how to summarize that, but effectively the problem is that if your working set fits in a larger than 25%, it works. But if it's bigger than even what you've allocated, then things start to get really weird. And again, what I was saying, it really reiterates that Postgres becomes more performance fragile in those cases. So then you really have to be sure what you're doing and make sure that you haven't, it becomes, you get a slight win from it, but you can get a big loss from it. So that's why we sort of tell people you can do it, just be careful what you're doing, because if your data size changes even a small amount, you may get into some very unpleasant performance behaviors. And you want to basically monitor what's going on to make sure you're not getting there. That pretty close? Yeah.
If you have a million rows from your query, does all of the data passes through shared memory?
So the question is, if you have a million rows, does all the data pass through shared memory? No. The way Postgres effectively works is that it opens what's called a portal, and it basically pulls rows from that portal, which may be doing a join or a sort or whatever, and then it funnels them out to out of the interface through libpq over the network, and it'll just keep pulling them. So as the older pages recycle out, they won't still be kept in shared memory.
They won't be kept, but they are passed through shared memory.
They're going to be passed through. Oh yeah, they're going to be passed, but not
Just the blocks that were needed.
just the blocks you needed, not the whole table. Yeah.
And of course, it's going to be way more than those number of rows you're joining and
Oh yeah. Oh yeah.
tens of millions of blocks to get.
Oh yeah. Yeah. You're going to have to churn through a lot of data if it's a big query. Yeah. They're all going to have to pass through at one point. There's no way to get at the data without that. Like that's the only way you have to see the data is through shared buffers.
Some other engines like Oracle have direct nodes, but Postgres don't.
That's correct. PGDump effectively just it opens a multi-statement transaction, and it says begin work, and it sets serializable isolation level, repeatable read isolation level, and it just does a big transaction. So there's nothing special about PGDump at all. It's just opening a big transaction, setting the isolation mode so that it gets a consistent snapshot across the entire backup, and then just runs it.
Where is the data for the PGConf? So it brings it into a shared.
So where does the data from the PGDump come from? Effectively, we prevent deletions, we prevent removal of expired data during PGDump. So even if somebody deletes some row, the row is still there for multiversion concurrency control, and PGDump can still see it. So it doesn't have to take a snapshot of the whole database. We just prevent removal of expired data while PGDump is running. And we can then reproduce a consistent snapshot across that entire database with no locks.
And so it brings in a table or data into shared buffer and then does the.
It's going to bring the table in, and it's going to sift through it and only show you rows that match the snapshot that you took at the beginning of the dump. Yeah. Yeah. But it never brings all of it in because it couldn't. Because some people think, does it just take a snapshot of everything and pull it into memory? It can't. That would never work. Yeah. So you're asking about the sort of cache wipe protection for sequential scans. So if you're scanning a table that I think is more than 25% of shared buffers, odds are you're going to read the front of it, and by the time you get to the end, you're not going to need the data at the beginning anyway. So if it's a big table, you're doing a big sequential scan, we will probably, we'll instead of reading it all in and wiping out everything in the cache, which is typically what we call a cache wipe, where a big sequential scan wipes everything. It basically takes like 16 8K pages, and it just cycles through those 16 8K pages, okay? So it doesn't interfere with everything, because we know it won't fit in the cache anyway. We know if you want to go back and look at it, you're going to have to read it anyway. So we might as well not wipe everything out. We go through a ring buffer, and in fact, there's something called, if you notice in the shared memory, there's something called synchronized scan. It's actually a shared memory like area. And if somebody else comes along and wants to do a similar sequential scan, they will start where the current sequential scan is running, go to the end, and then come back to the beginning again. So it's what we call a piggyback scan. And you avoid the problem of two people trying to do a large sequential scan at the same time. They would both be doing this ring buffer thing, right? And they would have to you'd be having to reread stuff that should have been in the cache. So the idea is if somebody's 50% in and somebody starts a sequential scan, their sequential scan starts at the 50% mark, goes to the end, and then goes back from 0 to 50% and reads the rest of the table. So that's a really nice cache wipe protection we've had for probably 5-7 years. Makes a big difference of that problem of wiping the cache, which can be very dangerous. Good. So I did want to cover this. I have 2 minutes left, so I'm not sure if we can really do it justice. I will say that this presentation is on my website, and I believe there are also recordings of this. But I'm just going to sort of show you 1 or 2 slides and highlight. You've seen this all before, so this all makes sense to you. You've seen these all before, effectively some setup. And what I'm going to show you is an example of the optimizer. This is what I wanted to show you here. Okay, so here's an example of a query that we're running that effectively is asking for specific constants in a table. A constant that's very common is a P. A constant that's very rare is a K. And what you can notice is the optimizer is automatically, for a very common value like a P, it knows to do a sequential scan. For a very rare value, a K, it knows to do an index scan. And in the middle, it knows to do a bitmap heap scan. Okay? So this is just a visible example of what effectively is happening when you have analyzed statistics. This ability to, where is it? To either analyze manually or let AutoVacuum run the analyze command to give statistics to the optimizer. Those are obviously super important in helping the optimizer do the right thing. Those are also super important when you're doing joins. So here's, for example, a nested loop. We've seen that. Here's a hash join. We've seen that. Here's a merge join. We've seen that. And again, depending on the type of query, the optimizer is automatically choosing the right join method. Here is the order of the fields doesn't matter. And then when we add statistics, we get different plans because now the optimizer knows better about what data is in these tables. Here we've gone from a merge join to a hash join, here's a nested loop. And if we create indexes, then we have additional optimization capabilities. So again, I'm sorry I can't go through it, but effectively, the idea behind this presentation is to sort of show you that optimizer in action and to show you how the statistics are used by the optimizer to produce the best plan. The bad news is we didn't get to this. The good news is we had a lot of really good questions. I think that's really what it's all about. Hearing me just talk and talk and talk is not super interesting, to me anyway. But anyway, your questions are obviously very interesting. And my goal was really to give you sort of a holistic view of what's inside the server, what does it do, how does it do it, what are some of the design decisions we have, how does it sort of fit together, and hopefully you have a better understanding of how that works, and a better understanding as you use Postgres of what it's doing and sort of how you can help it and maybe understand how to make it work better. Okay, so thank you very much. Appreciate it. We are out of time. Thank you for your promptness, and it's been a joy doing this class with you. Thank you.